Good morning, everyone, and welcome to our workshop. And the name of the workshop is Data-Centric Robotics. What data do robots really need? And thanks for coming out so early on a Friday. And today we want to dig into a big question in robot learning right now. What data do robots really need? And let's get started. And yeah. Let me start with why we are all here. Image and vision models have been taking off, and mostly because they are training on huge amounts of internet data. And the robotics is now at a similar point, but the main thing holding us back isn't just models or compute, it's data. How much we have and how good it is. And the problem is there's no internet for robots, no shared large-scale source of robot data. So the question for today is, what data matters most for training robots and how much is enough? We'll look at this from a few angles, where data comes from, scale laws, and how to build and curate data sets, and how to evaluate, and how robots can keep learning after they are out in the world. And we want it to be a real discussion, so please jump in with questions. And here is today's agenda. We'll start with 4 invited talks from Ashwin, Balakrishna, Hao Zhiqi, Simar Kareer, and Wenlong Huang. And we will also have a cover break and poster session, followed by 3 spotlight talks and a panel discussion, and finally the award ceremony and closing remarks. And we received and accepted 34 papers for the workshop, and the poster session will take place during the coffee break from 10:05 to 10:35, just outside the room. And the 3 papers were selected for 5-minute spotlight talks, and the 1 best paper award will be announced during the closing remarks. And before moving on, I would like to thank all the organizers for their work on the program, review, speaker coordination, and website, and logistics. And this workshop would not have been possible without everyone's effort. And we would also like to thank our sponsor, Spirit AI, for supporting this workshop. Their support help us bring the community together and create more opportunities for discussion around data-centric robot learning. And okay, let's get to our first talk. It's my pleasure to introduce Ashwin Balakrishna from Physical Intelligence, where he works on large-scale robot data collection and evaluation. Before that, he was at Google DeepMind on the Gemini Robotics team. He did his PhD at UC Berkeley and his bachelor at Caltech. And his work is all about scaling robot data. So this is a great way to kick things off. And Ashwin, and over to you.
Cool. Yeah, thank you very much for the kind introduction. Pleasure to be here. Let's cut off a little corner.
Okay.
Oh, cool. Yeah, thank you very much for the kind introduction. It's a pleasure to be here. I'm Ashwin. I'm a researcher at Physical Intelligence, working on robot data scaling. And today I'll be talking about the role of data in our latest robot foundation model, π₀.₇. So let's start by taking a journey way back to the dark ages of 2022. And as ridiculous as that sounds, machine learning looked very different back then. So here, even in digital AI, right, if you wanted, say, a video captioning model or a code generation model or an image segmentation model, typically what you would do is you would go on a hunt and find the best recently trained model for that specific task. And then you'd use it and it would work pretty well. So high-performing models did exist for various different tasks, but they were task-specific. They had one job, and they typically did them pretty well. But fast forward to today, and we live in like a very different world, right? So we have like single models, like say like Gemini or Claude or GPT, which can do like many different tasks very well, often just as well as specialist models for things like segmentation or video understanding and things like that. So what's the point of having like one model that can do tons of different tasks like this? So the obvious answer is it's just convenient and scalable, right? So on the system maintainer side, right, you just have one set of weights, you have one system that can do lots of different things, which is nice. And also from a user perspective, right, you don't have to go on a hunt to figure out like which model to use anymore. You can kind of be confident that for like a pretty wide range of tasks, like ChatGPT is going to be able to do the job. But there's actually more to this. So there's a hidden benefit, which is what I'll call compositional generalization. So basically learning many tasks, having one model that's trained to do many, many different things actually allows you to compose capabilities from those different tasks to actually do new things. So really here, like, the whole is better than the sum of its parts. So let's consider like a simple case study here. So consider object detection, for example. So you can, of course, train a specialist model to detect objects with the right data. And you can also easily get modern VLMs to do this task too by either training them with the same type of data or distilling these specialist models into the modern VLMs. But the cool thing with modern VLMs is they're also trained on lots of other tasks. So for example, modern VLMs are also trained on, generating code, for example. So I think this is explained. So yeah. So you can do like cool things. Like, for example, you can like interactively write code to detect tons of different objects in an image to like answer a question, like the reading of the stage. So this is actually like an emergent capability, right? So the model wasn't trained to do this, but because it's trained on object detection and code writing, it can compose these capabilities to do something fundamentally new. So at this point, you might be wondering like what any of this has to do with robotics. So I would argue that, in the last few years, in actually trying to develop robot foundation models, there's been this kind of tension between trying to build, models that have high performance on tasks, but also models that have like a wide breadth of capabilities. So we started out with methods like diffusion policy or ACT, which were super exciting and showed like the first signs that you could train models to do specific tasks really well. And these were often like tasks that were like much more dexterous and complicated than people had ever seen robots do before. So this was like a big jump. Concurrently, there was also work like RT2, for example, showing the first flickers of life for like true robot foundation models. So models that could do tons of different tasks, but these tasks often ended up being like relatively simple, like pick and place type tasks at like low degrees of reliability at the time. Concurrently, we had further work from various companies and academia as well, showing that we could actually push the boundary even more on doing tasks that are like super dexterous, much more realistic, closer to tasks that people might actually want fully automated, like packaging a full item end to end over and over again, or like making coffee for like 10 hours in a row. So this was exciting as well, but still these models were limited to doing single tasks, but they could do them at relatively high degrees of reliability, and the tasks started to become more and more realistic. Concurrently, there was also further progress on training models that could like follow instructions in a very like flexible way, but still these models required task-specific post-training to do any given task that was realistic at a relatively high degree of reliability. So what we've been missing is kind of something over here. So a model that can do a wide range of different tasks, but also can do tasks that are like, realistic, dexterous, and actually do those tasks at high performance with high reliability. And this is the niche that π₀.₇ tries to fill. So this is one model that can do lots of different tasks, and each of these tasks are often like dexterous, long horizon. It can do these tasks at relatively high degrees of reliability as well. So in our previous release at pi*06, the contribution was a new RL post-training recipe to do a variety of different complex long horizon tasks at relatively high degrees of reliability and throughput as well. So these are tasks like laundry folding, making espresso, folding a box. But a cool result in π₀.7 is we just ended up having one model that could just do all these tasks directly out of the box. So this is just a single model with no task-specific post-training. And it could often match the success rates and sometimes even outperform π₀.₇ in terms of throughput. But one cool thing about π₀.₇ is it's also trained on just tons of other tasks. So there's like many other tasks too, like making a peanut butter sandwich or taking out the trash or slicing zucchini or peeling fruits and vegetables that π₀.₇ can also do at like relatively high degrees of reliability. So this is like the first contribution of π₀.₇. So it's like one model with a wide range of different dexterous capabilities. So what are like the ingredients of π₀.₇? So how did we do this? So the first ingredient is, will come as a surprise to no one here, is super diverse robot data. So this is both demonstration data and also autonomous data that we collected from actually evaluating our robots. But the key insight in π₀.₇ was just having super diverse robot data wasn't actually enough to actually effectively learn from all this data. What we needed was really rich metadata. And this metadata gave us information not just about what these tasks were in our data, but also how the tasks were actually performed. So this included things like detailed language annotations describing exactly how the task was done, quality labels that described like when mistakes happened or like how high quality the overall episode was, and even like generated sub-goals that gave more detail on like how exactly the task should be performed rather than just, a more coarse language description. And one cool thing we realized is having this metadata actually allowed us to scale robot data collection much more effectively and learn from mixed quality data. So kind of the subtext here is when you're like really scaling a robot data collection operation, you're inevitably going to have some low quality data like we see on the right here, right? If you like have like, hundreds of different like operators collecting data, there's going to be some data that's like a sloppy fold like this, for example. But the cool thing is if you actually have metadata that's like very carefully annotating, why certain behaviors were low performing, then you can actually effectively learn from all this low quality data quite effectively. So on the left here, we have a plot where we use the π₀.₇ recipe and trained a model just on laundry folding data here. And you can see from the left to right, we're including larger and larger splits of data where the average quality of the data is actually going down. So like the first 30% of data is like super high quality based on our like post-hoc quality annotations. Then the next 50% is like slightly lower quality. And then like as we introduce more and more data, we're introducing more and more low quality data. And we see that if we train π₀.₇ without metadata, actually like performance can get worse as we train on more data. And this is kind of unsurprising, right? Because we're just mimicking what's in the data. And if our data is getting worse and worse, then it kind of makes sense that the model would also get worse. But if we condition π₀.₇ on metadata describing a lot of detail about the quality of the data, like a lot of detail about how exactly the tasks were performed, then we can actually improve as we train with more data, even if the average quality of the data is going down, because now at test time, we can just ask for good behavior, right? So this is kind of analogous to like when you're playing with Claude Code and just say like, make no mistakes, that can actually lead to better performance. And we found that in some ablations we ran that training with metadata and training with evaluation data were both super important. So here we see that if we train π₀.₇ without any of the evaluation data that we actually collected from evaluating our models on specific tasks, like here we consider all the tasks we considered in π₀.₇, performance goes down. So we see that π₀.₇ can actually effectively leverage suboptimal eval data, which is also on policy, which helps to improve performance, but only if that data is actually paired with metadata describing why those behaviors were low performing. So we found this to be exciting. And so far, I've talked about π₀.₇ as like one model that can do lots of different things, which is great and all. But as we talked about in the digital AI example in the beginning, the real benefit of having one model that can do tons of different tasks is emergent capabilities that you get from composing behaviors from those different tasks to actually do new things that you didn't actually explicitly train the model to do. So I'm going to be talking about 3 emergent capabilities we observed when just playing around with π₀.₇. So the first one is compositional instruction generalization, or the capability of a model to compose instructions that it's seen in different contexts to do slightly different tasks from what it's seen before. So here we'll consider 2 tasks. So we had data, in our like large training mix of 2 tasks among many other tasks. One of them was a busing task, where you're taking trash and putting it in a trash can and taking dishes and putting it in a busing bin. And another one was like a natural thing you might do in a kitchen, moving food from like a fridge to a microwave. But one fun thing we wanted to do is we wanted to see if we could actually see if π₀.₇ could do tasks that like involved similar instructions, but involve composing them in like fundamentally different ways. So we were testing actually a particularly like nefarious form of compositional instruction generalization. We tried to see if we could do like reverse busing. So this is like taking trash and putting it in the busing bin and taking dishes and putting them in the trash can, which like of course doesn't make any sense. Or like a reverse version of this fridge to microwave task. So moving food from the microwave to the fridge. So this is typically challenging because this is breaking strong biases in our data set. And of course, like we're biasing towards collecting realistic data, so we would never collect data for tasks like this on the right. But the cool thing is we found that π₀.₇ was actually pretty good at doing these tasks. So we could actually prompt it to perform these tasks, even though they broke the biases in the training data. While our previous models, π₀.5 and π₀.6, struggled quite a bit. So we found this quite exciting, and it suggested that π₀.7 could actually very carefully ground its behaviors in detailed instructions that we provided. And the more exciting thing, actually, is we found that this also unlocked open-ended language following in unseen environments. So previously in π₀.5 and π₀.6, we saw strong signs that we could get our models to do seen tasks in unseen environments. But now with π₀.7, we actually just tested our model on like a bunch of freeform, like dozens of different freeform language prompts, also in unseen environments. And we found that in this case, like π₀.7 was much better at like following these open-ended instructions in a number of unseen kitchens and bedrooms than our previous models, π₀.5 and π₀.6. The second emergent capability we observed was compositional embodiment generalization, which also is known as like cross-embodiment transfer. So what I mean by this is we might have some data of doing a task, say folding a shirt on embodiment A. So here, in that case, it's like an arc firearm station. We might also have data generally of like controlling a robot to do other tasks. So in this case, this UR5 firearm station on the right, we've seen a lot of data of like, collecting, like tons of other tasks, but we've never actually collected any like laundry data on this task. And what we want to test is like, can π₀.7 compose its abilities to do, a certain task on the source embodiment and its general capability of controlling the target embodiment to do other things to actually do that task on the target embodiment. So in this case, we'd be checking, can π₀.7 just like zero-shot control this UR5 firearm station to fold shirts, even though it's never seen shirt folding data on a UR5 firearm station. So one cool thing we actually noticed in this investigation is that cross-embodiment transfer actually emerged as a natural property as our models got better and better. So the first setting we considered was this like super simple table setting task. We're basically just like rearranging objects on a table. And in many ways, this is like one of the easiest settings you can consider for cross-embodiment transfer, because not only is the task relatively simple, but also we collected data for this task on like a bunch of different embodiments. So it's like kind of easier to learn like a shared understanding across these embodiments of like what it needs to perform this task. And then we tried to evaluate on a held out embodiment. And we found that like π₀.7 did pretty well, but so did our previous models. Then we made things a little bit harder. So we considered some tasks where we collected data on a bimanual UR5 station, and then tested π₀.7 on our bimanual ARC stations. So here we see that π₀.7 does well, and the gap between π₀.7 and our previous models is starting to get greater. Then we like up the ante even more. So now we considered a task where data was only collected on a bimanual ARC station for the shirt bagging task, and then we tried to get π₀.7 to do it on a single arm UR5 station. So now you need like a fundamentally different manipulation primitive to even be able to do this task. And here we see like the gap getting even bigger. Then we made it even harder, where we considered a setting where we were actually trying to get π₀.7 to do much more dexterous tasks. So these are often much more sensitive to embodiment differences. So for context, like we only ever collect laundry data at pi on our ARC's biarm stations, but we tried to see if π₀.7 could still, fold a towel or fold shirts on our bimanual UR5 stations. And we found that here there was like a pretty big gap between π₀.7 and our previous models. And this was kind of cool because like on these different stations, you need like a pretty different strategy to fold shirts or like fold towels. Because for example, on like ARC biarm stations, like often people would like approach like the shirts from like the side with the grippers, but like on a UR5, it's like way more bulky and like you often have to like have much more top-down process. We found this exciting as well. And one cool experiment we did is it's actually like really hard to even teleop the UR5 biarm station. So like a bunch of us researchers tried it and like we were just like horrible. Our teleoperators were like a lot better than us. But still we found that like actually even like the human level like performance for like teleoperating the robot to fold shirts on a UR5 bioarm station was pretty comparable to our models just zero shot on the UR5 bioarm station. So that's kind of cool because it suggests that like one way to get a model to do tasks on an embodiment where it's really hard to even collect any teleop data is to rely on emergent cross-embodiment transfer. So we found this to be, an exciting practical implication of this result. The final emergent capability I'll talk about is compositional task generalization. So here we're just trying to see if we can get π₀.₇ to do a task that's like different from any of the tasks it's ever seen in its training data. So first we considered a task where we wanted to see if π₀.₇ could load a sweet potato in air fryer. So first we like literally just asked π₀.₇ to do this. So we just typed in load the sweet potato in the air fryer and try to see what happened. And unsurprisingly, like this didn't work, though there were like reasonable signs of life. It's able to get the sweet potato into the air fryer. It wasn't able to like actually close the air fryer, as you can see here. But it's not bad. You see flickers of life. But one cool thing we found is if we actually coached π₀.₇, and what I mean by that is like if we broke down this task into its like constituent components, then we found that π₀.₇ actually could fully do this task pretty reliably too. So this is kind of akin to like chain of thought prompting with like very early language models where like if you broke down tasks in detail for these language models, you could actually coax them to do tasks like pretty different from what they'd seen before because you're like breaking them down into like pieces that they could like, connect to their training data and compose of them. And we found that generally π₀.₇ was just a lot more coachable for a variety of these different held out tasks than our previous models. So if we actually broke down these tasks in detail, we could get π₀.₇ to do like a bunch of different things they'd never seen before, like loading an air fryer, unloading an air fryer, like toasting a bagel, things like that. And one cool thing actually about this like coaching process is it actually allows you to effectively collect data to train a high-level policy that can just replace the human's role here, right? So now you can train a high-level policy to just prompt π₀.₇ instead. And the cool practical implication of that now is if you do that, you can actually teach π₀.₇ to do new tasks without collecting any teleoperation data, as long as the task is not like too out of distribution from what it's seen. Because if you collect these coaching demos, you can just train a high-level policy to prompt π₀.₇ just as you might. And we found that for a variety of different tasks, we could actually generate autonomous policies with this procedure that perform quite similarly to π₀.₇ when we just coach with human feedback. Yeah, that's π₀.₇. We're pretty excited about the results. And although this is all still early and there's a lot of room to improve, we're excited about seeing the first signs of compositional generalization in various ways, and think this is an important step towards creating generalist robot foundation models that could be broadly useful for a variety of tasks. I also want to acknowledge all my awesome collaborators at Pi. This was work with all of us. And yeah, with that, happy to take any questions. Thank you. Yeah.
And what's amount of data for textures class example t-shirt?
Yeah, so the question was about the amount of data used in pre-training and the amount of data used for Dexterous tests. Unfortunately, I can't give you a number on hours of data used. Yeah, but I can talk more about the different training methods used and stuff like that. But yeah, I can't describe the exact number of hours.
So each portion account for 100%, 1% of the data.
Yeah, I mean it's it's a relatively small percentage. So we train on data from a very diverse set of tasks. So laundry folding initially was a large portion of our mix because in our earlier models π₀, π₀5, that was a very significant part of what we evaled on. But increasingly laundry folding is becoming a much smaller portion of our overall pre-training mix because we're trying to make sure our model can do thousands of different realistic tasks, homes, business settings, things like that. Yes.
To the top, I think metadata. Like it seems like the structure is category. If thoughts on how
Yeah. So the question is that some of the metadata we conditioned on was like, categorical in style, like, quality labels like 1 to 5. And is there a way that we could transition that all to language? And I think, yeah, like totally we could do that. And that is something we're exploring now. I do believe that that would probably help. This was just like something early that like worked pretty well. But in general, like we also found that like super detailed language annotations went like a long way. So if we could like mix this quality information just into that like language string, I think like that probably would lead to like even more promptability than we're seeing right now. Yes.
Yeah. What do you think is for the pre-train? What is what kind of data is good pre-treated and what kind of data is good post-treated? And is there two kind of data the same? And the second is in the slides you show that in some tasks the goal condition π₀.₇ performs much better than the original like the language prompting purposes. So if what kind of situations do the goal condition one performs better than the machine?
Yeah. So actually, can you remind me the first question? Pre-training versus post-training. Yeah. So
Yeah. What's the characteristics of the pre-training?
Yeah. So the first question was about the characteristics of like good pre-training data versus post-training data. Generally, good pre-training data is just like very, very diverse. And there's like diversity both in like the tasks you're doing, the strategies you're following, like all of these things. And the key insight we found in π₀.₇ is that like I think before, like both within Pi and as a community, right, like a lot of what we try to do to get robot foundation models to work well would be like very careful data curation to make sure we always have like the highest quality data possible. But we actually found that like that's kind of at odds with like scaling a data collection operation, right? Like you can't rely on that. So what we found is that like for pre-training data, it is actually important to just do something that can scale efficiently. And make sure that you collect like maximum diversity across like every axis you can think of, and then actually make sure that you can like disambiguate that multimodality with like detailed labels that like describe what all those differences look like so your policy isn't blind to them. So that's like the main insight we found there. For post-training, we still find that like collecting much more like narrow task-specific mixes that are like more like uniform and like their strategy behaviors are most useful. For your second question, yeah, we found that like there were certain tasks where like goal conditioning helped a lot over like a traditional language condition policy. And those tasks were mainly like, it was mainly on the cross embodiment side because like we found that like, these like goal generation models were like really good at just like translating between embodiments, which is like unsurprising. And because they could kind of like translate an image between embodiments, then like it made it like much easier given that image for like our low level policy to actually know what action chunk to output. So that was like a big area where we found lift. And then another lift that we found was like in the cases where we were trying to test like compositional instruction generalizations, we were trying to like break super strong data set biases. There we also found it useful to use like an external goal generation model that wasn't like, hamstrung by the same biases that exist in our robot data. So you could actually break that, follow a language instruction very carefully to generate the right goal image, and then condition on that goal image. It's like much easier to actually follow that and generate the right action.
So much for that. Follow-up question is that with this huge amount of version data, how did you get the metadata for the huge amount of version data? And like the quality of the data, you have like high quality, medium quality, and low quality. And how do you like get those labels right?
Yeah. So the question is like, how do we get quality annotations?
So much money, so much money.
Yeah, so the nice thing is like I guess we can set up like large scale annotation pipelines. So we have like external vendors we work with, that we like of course do like very careful QA with as well, to make sure that like the quality labels align with what we think as researchers. But yeah, I guess that's the nice thing that we can actually do like super large labeling at scale. and ask annotators not only to like describe like in a lot of detail, like in language, like what actually happened, but also like, you know, explain like, oh, like, you know, was there like something dropped, or like we can give them like very detailed instructions on like how to label quality, and we find that that helps a lot. Yeah.
So, generate most
Yeah, it's a mix. So as you might imagine, like initially most of this labeling is done by humans. And then like recently we've been trying more and more to like make this autonomous, because like we've collected like a critical mass of, you know, quality data that like kind of reflects our opinions as researchers about like what the data looks like, that we can kind of ingest this into like run models as well.
About those cultivators, are those more about the action? Like, is there some on the specs and low quality of the action data, or the language, or the
Yeah, so this is mostly on the action side. So there's like separate things that we would do to make sure like, okay, like our operators like just following the right instruction, are they doing the right task, have they like set things up correctly? So that's like kind of a separate QA process. But it's more a matter of like, you know, was like a mistake made in a grasp? So like there'll be like annotations we collect like on an episode level, just saying like, oh, generally like was it shortfall good, or like was it super complete? And there's also like similar annotations we'll collect at like a segmented level, much more detailed than an episode. We'll be like, oh, like in this section, with some small mistake. Yeah.
I wonder about that. And so let's say you ask to for context of some policy you know, and after like it's the person too you actually think about and like address the dynamics of the features
I see. Yeah, so the question is like, how do you deal with like if you've collected a bunch of data of like just pouring something into a bowl, and then like test time you like move the bowl, like how do you know that's gonna work? Yeah, so we like don't do like anything explicit to deal with that like precise situation. But the thing is like, since we've collected like such diverse data across like tons of different tasks, like even if we have like a specific task that we collected and put in pre-training where like, you know, you're pouring, you know, something into a bowl in a fixed position, we've like probably poured something into other things in like a variety of other positions. So we find that like, you know, our model can typically interpolate quite well. It is quite robust, like object positions and that type of thing. Yeah.
What the particular type of the and that's the function that gets
Yeah, so the question is about the modalities that we feed to the model. So the model takes as input a language string describing what task it needs to do. It takes as input typically like 4 images, so like wrist camera images, like an overhead base camera image, and then like sometimes like a backward facing image too, if it's like one of our mobile robots, just giving it like a global view of the scene. And then given that, like, and then sometimes we'll also like provide it like a generated subgoal image, as we saw here. And then given that, it like outputs an action chunk. So we don't like explicitly track like object positions or anything like that, and we don't like have like explicit depth information in the models either, as you referred to. Depth, we often find that we can kind of like implicitly figure out from like multi-view images. And in terms of like object positions, we find that like it's like pretty hard to like track those reliably, and like you can often infer the information you need for the task if you have like enough data generally. So we don't like track them with that explicitly. Yeah.
I found like cross-embodiment transfer interesting, especially the bimanual and single art. Have you found any like limits of what you can generalize cross-embodiment to?
Yeah, so the questions are regarding the limits of cross-embodiment generalization. So for sure, yeah, I mean, there are limits. So what you saw for like the bimanual to like single arm transfer was like a task where still like you do need like a different manipulation strategy in the sense that like, okay, to bag this shirt, like you have to realize that like, oh, you only use like one arm to like pick it up and put in the bag. But I expect for like tasks that like require like really dexterous behaviors and you need like a dramatically different strategy. Like for example, maybe you have a task where you needed to like hold something down with one arm while like doing something with the other arm. And then like you suddenly decided to like see if like π₀.₇ could do it with one arm. And the only way it could do that is like by using like the elbow of like that one arm to like hold something. That like definitely like wouldn't work yet. So there's like definitely limits where we basically find it's like a function of like how dramatically different the strategy you would need to follow is to actually adapt to that embodiment. And a lot of the experiments you saw where we're testing like UR5 to ARCs transfer or vice versa kind of involved like adapting to like the effective like weight and controller differences between the robots. And then sometimes like number of arms too. Oh, yep. Yeah, that's a great question. So the question is that like π₀ had advantage conditioning, π₀7 does not. What's the reason? So we found actually that I guess like advantage conditioning like does give you like more information, of course. And there like you're conditioning under advantages that were grounded in rewards that basically told us like the number of steps, right? Like until completion. What we found in π₀7 is that like actually conditioning on like a bunch of other information beyond this number of steps was like quite useful. But I think like a natural next step is to now see like, okay, if we can construct like a global reward function with all the information that we found was useful in π₀7 and then do advantage conditioning with respect to that, like maybe we'll see like even further gains in performance. So that's definitely something we're going to try next. Yeah. Yeah. So the question is like, have we run an ablation where we actually train our policy just on the best data instead of like including all the data that's lower quality? And that's like kind of the result that was shown in the scaling plot here. So here we see that like, training just on like a higher quality split does like reasonably well, but we can actually get better training on low quality data. Now, of course, this isn't exactly controlling for amount of data. So maybe like the most precise way to do this experiment would be like you train on like the same amount of like all high quality data versus like a mix of data quality. That we haven't done exactly. Any other questions? Also happy to turn it over if we're out of time.
Okay. Thanks, Ashwin, for your wonderful presentation. Okay. Okay, I can see you and hear you. Okay, great. Okay, great. Over to you.
Okay, great. So can the people in the room hear me?
Yes. Yes.
Okay,
We can
sounds
hear you.
good. Okay, then I'll just start. Hello, everyone. My name is Haozhi, and thank you for the organizer for the kind introduction and for inviting me. I really hope I can be there in person, but unfortunately cannot make it this time. But still, I'm very excited to talk about my research on dexterous manipulation. Let me start by saying I think probably most people in this room would love to have a robot in our homes, of course. So this robot should be able to handle every chores such as cooking and laundry so that while they are doing the task and we can enjoy our life. And to achieve this, my research is really centered around how do we build algorithms and systems that can give robots human-level dexterity with human-like hands, just as the talk title indicates. And of course, you might ask, why bother? Because we can already get amazing results with simple anti-factors. Ashwin was talking about π₀7, and there is also a recent release of Generalist AI that is really exciting and demonstrating capabilities we haven't imagined 5 years ago. And of course, I'm also curious about this question. And to argue for my point of using Dexterous hand, I also did a very simple experiment. So here is a video in which I directly control, a pair of tongs, which you can consider it as a pair of grippers. I think the video is kind of laggy, but it's a kind of, you can imagine it's a one popular choice of specialized and effectors in our current community. Then to perform a very simple task, just trying to cutting this apple. And now the point of this video is that all the vision and other like reasoning tasks are already solved because it's directly operated by hand by a human. So, but as you can see, it's not an easy task. So picking up the knife requires some careful strategies. And after picking it up, cutting this apple, applying the right amount of force is even more challenging. Well, on the other hand, we human can easily do this even without any considerations. So because these tools are designed for our hand, and we also have like a lot of sensory informations, including vision and tactile sensings to help us, in this case, to make decisions and executions. So this contrast make me think that if we ever want to build intelligent robots to coexist with us in our homes and help us with tasks we are interested in, they need to interact with the objects, the environments, or the tools that is designed for humans. So therefore, they must be equipped with multi-finger hands. And of course, however, although theoretically this dexterous hand offers lots of flexibilities, building the dexterities is not as easy as swapping the end effectors and apply the same recipes. And there are several reasons. Firstly, the hardware is not as reliable and as mechanically simple as parallel jaw grippers. And it's naturally get higher degree of freedoms and requires some complicated coordinations between your wrist, your fingers. And also, one reason we want to use hand is we want to make the manipulations more efficient. And if you want to do that, the manipulation strategies will require more complicated patterns. So all of this does not only introduce problem of policy learning or hardware design, but more importantly, these challenges make human harder to control either by teleop or wearable devices to control to the robot. So making data collection and scaling much more harder. And in the past, I'm trying to see what is the right way of scaling up data for dexterous manipulation. I have been mostly working on using simulator as a data engine and training reinforcement learning algorithm inside simulation and transfer that to the real world. So I have demonstrated several works on mostly in-hand manipulations on diverse objects. And the paradigm is pretty standard right now. Just to give some context, we basically use large-scale parallel simulations to generate a lot of data. It contains maybe thousands or tens of thousands of robots simultaneously interacting with the environments and generate data like tens of thousands times faster than real-world data collection systems. And each of the robots shown here hold maybe a randomized objects in terms of size, physical properties, and we can apply pretty off-the-shelf RL algorithms and to fit into these training distributions. And by seeing lots of distributions, the learned policy can be quite robust and generalizable to different situations and to the real world. So for example, this is early days when we released the code. Colleagues from University of Bristol, they can directly download code and deploy our policies in their slightly different robot hand. In like a few years, in 2022, this is not commonly seen for a dexterous hand project. And we have also been able to bring this robot to different places, such as this is in Coral, real world demo of this hand rotating orange peel. Or sometimes there are also audience trying to hand over some irregular and thin objects from their package, such as this iPhone charger. And this, I mean, this basically shows this paradigm can give us some robustness performance in the real world. But meanwhile, it's definitely not going to be a gold standard by just using this one single data engine paradigm. It has been extremely successful in terms of making policy robust, but it is also, there are many challenges behind the scene. For example, usually these policies are learned each task by each task. For each task, one need to carefully design the reward, and there are also some system level engineering to make it happen. And in simulation, it's also not easy to simulate all kinds of sensings we can see in the real world, such as tactile sensing is one of the difficulty for simulation. And then we also suffer from the sim to real gap a lot in terms of the context modeling in simulation might be different from the real world context. And there are also some dynamics gaps that is even unmodeled. So in this talk, I'm basically trying to show some of my recent work that trying to combine the advantage of simulation as well as other alternative data collection paradigms to achieve better performance and then advance the Dexterous manipulation capabilities. For example, when we consider alternative data collection paradigms, you can easily think about learning from teleoperation data, which has the advantage of there's no embodiment gap. What you can collect is directly can be learned a policy on the real world and then deploy this policy in the real world. However, teleoperation has its own problems. So, and especially for Dexterous hand, teleoperating this hand can be extremely difficult, much more difficult compared to teleoperating grippers. And I'll show examples in a minute. And on the other hand, there's also a very popular recent alternative is directly learning from human videos. It's very scalable. It's also very and one of the reasons we can argue for Dexterous hand is it's very similar to human hands, and then it would be much better if we can directly learning from human doing stuff and then transfer to the robot hand. However, there are also challenges because learning from human videos, we cannot directly get the action labels or the dynamically feasible trajectories from human video. Because either when you're learning from human videos, you can either use vision techniques or maybe wearable devices, which mostly gives you joint positions instead of the actions and the contact forces like during these manipulation tasks. And more related to this argument, there's also no forceful interactions can be captured when naively doing learning from human videos. And in this talk, I will introduce several works trying to address each of these challenges. So the first work, I'm going to talk about why teleoperating Dexterous hand is difficult. So I'll give you two videos. The first one is what you just see is a RL policy that doing this. Nowadays, we consider as a simple in-hand manipulation task. Well, on the right-hand side this is myself trying to teleoperating the sharper hand and using some very advanced, accurate exoskeletons. And this, sharper hand for the context is also one of the most advanced Dexterous hand for now. And they, of course, doing careful engineering to minimize the latencies between your exoskeleton signals versus sending command to your hand. But it's still quite difficult. And this is because this teleoperation interface for human is very unintuitive. So because this task requires a lot of finger coordinations, we need to actively thinking about when I want to do some motions, which fingertip I should move and which fingertip I should stay there, and which one I should apply some penetration forces so that the objects can be stably in hand. So this is even for me. I also did some teleoperation works before and having some experience of that. It's still quite difficult. So in the first work, we are trying to see, you can imagine doing that is hard, maybe doing some more complicated tasks like screwdriving or nut bolts assembly is also quite challenging if we are doing teleoperation. And then I'm going to show how we do that. And the idea is just to use a combination of teleoperation and learning from the real world data, and also using simulation as a skill primitive. And the idea is, there are several steps in our pipeline. So firstly, we are going to train an RL policy in simulation. So the recipe is pretty standard for training in-hand manipulation or even locomotion policies. You just design some observations and then feed into off-the-shelf policy algorithms. And then one caveat is that if you want to deal with the task of nut bolt or screwdriving, modeling the environment, like the complicated thread structures of these tools and these interactions between tools and the environments may be complicated. So in this work, we take an alternative approach to use simplified environments. For example, we can model these tools or interactions between tools and the environment as a simple revolute joint. So there are two linkages, and this linkage is connected by this rotational joint, and this upper linkage can move, and while the bottom linkage cannot move. So this is not an accurate object from the perspective of simulation. But if we directly use these objects to ask a robot to learn the rotation behavior, it can successfully learn the motions. And this is what we call imperfect physics. And it's also in the sense that the asset modeling is not what exactly we are going to do in the real world. And it's also including that we are not going to simulate tactile sensings in this simulation. And this current policies is only learn a coarse motion that can rotate these linkages. Then there are a few reasons why we do that. The first reason is doing that is just making your learning much faster. So by simplifying dynamics, by just making the simulation task easier. And there's another reason is that now the goal of this policy is not to learn a purely autonomous policy that can directly transfer to the real world. Instead, we are just treating it as a skill primitive, so that the teleoperator can doing some fine-grained human-in-the-loop adjustment to make this imperfect policy that can work in the real world. And more specifically, we are going to enter the second stage. So there will be a human teleoperator. The human teleoperator control two things. The first one is that it will control the wrist movement, similar to all the other teleoperators. And secondly, it also controls whether to activate the RL policy. And the RL policy will output the finger coordination signals, all the actions. So if you recall, just a few slides ago, I said finger coordinations is quite challenging, but now we do not ask the teleoperator to do that. Instead, we ask the teleoperator, we basically delegate this finger control to the policy, while we just ask the human teleoperator to abstract one level above to control some high-level intentions and movements of the whole robot. And it also has the advantage of now we collect the data in the real world. We can therefore collect tactile responses that is not simulatable, but it will be very useful for our real-world tasks. And the interface will look like this. So you see this the Quest controller is you cannot use a Quest controller to control each of the fingers, but you can use it to control the wrist movement. You can also control it to decide which time step you're going to activate these finger coordinations and then to rotate this nut bolt. And after you get this, it's a quite easy to control interface. And then you can just quite easily collect a bunch of trajectories so that you can directly training a tactile aware policy just using your favorite behavior cloning algorithms, either ACT or diffusion policies. And then this will become our final policy that we show this policy can autonomously finish this nut bolt in the real world. So this is one of the examples. And our policy currently does not have any vision as input. It only relies on the tactile as the signals. So it can easily generalize to other type of objects, other type of nuts that we did not train on. And this is basically because the tactile signals is very local sensing. After it learns the context signals, it will basically transfer to. So although these two nuts they appear from the vision perspective is very different, but the context signals is pretty close to each other. And of course, we also did some comparisons between tactile and non-tactile policies. So this tactile is just very similar to what you have seen before, but without tactile, initially it can still roughly finish this task in a few revolutions. But if without tactile, there's no signal tell the policy what is the relative position between the nut and the fingertips, so that gradually when the nut is going down, it cannot sense where is the nut. And using the similar pipeline, we can also do slightly more complicated tasks like doing this screwdriving task, following the similar paradigm. And the summary of this project and what we learned in this project is we can delegate different things, delegate requirement to different data engines. We can use simulation to learn complex, reactive, and short horizon skills. And it can be combined with human teleoperation. And there are basically two advantages. Firstly, the data you can collect can be much more complicated. And another advantage is that now your sim-to-real transfer policy requires less tuning because there will be a human provide online corrections during deployment. Okay, and I'm going to switch to the other side, which is the growing interest on the human data. And this is a very promising direction, of course, because there are many desired properties that we want for robots. Like there are super diverse, abundant data in the internet. It's also easy to collect at scale. It's also very rich in terms of high-level intent and task structures. And of course, it's very aligned with robot hands. Like the difference between human hand and robot hand is definitely much smaller than other end effectors. But of course, there are still a way to go. There are still several challenges we need to conquer before we can really finish this dream. For example, you cannot get action labels because what you can get from human data is not the force, it's only the positions of your human hand. So this is the reason we study in this work called Spider, which we are trying to towards one step building algorithm that can turn in human motions to a robot actions. And typically how people do that. So firstly, starting from some human videos. And then we are so typically people will try to do some trajectory extraction method. So it can either be computer vision method by detecting and 3D reconstruct the object mesh and also reconstruct the human hand. And so trying to turn this video to a 4D trajectories. It's a 3D plus the time axis. And then to mapping the human hand to robot hand, there is also a step of kinematic retargeting that is showing on the right that there's trying to in the either simulation or in other visualizers, so they can turn this into a visually looking good robot trajectories. However, this pipeline is often infeasible in practice because there are a lot of noises when you capture this human hand, robot hand, and also you are not sure whether this human hand, whether you can get the action labels just by looking at the position signals. So in this paper, we are trying to use simulation to make retargeting physically plausible. By physically plausible, we basically means if we have these trajectories, we can execute these trajectories either in simulation or in the real world, so that the objects' motions will achieve the objects will achieve similar motions as we see in the real world. And the high-level pipeline will look like this. So like the first step would be still like exactly the same as previously what people are doing. We give a human data, we have a reconstruction method to get human motion, robot motion, and object motions. And what is different here is that we put the whole scene in a simulator and then using sampling-based method like MPC to sample the actions. So you can imagine at each time step, we are going to sample a lot of actions. And of course, because this is in simulation, for each action, we can step the environment just to step the environment and check whether this action will result in good behavior or bad behavior. And good behavior is defined basically as whether the objects move in terms of aligned with the reference trajectories or it's not, or maybe just falling down. And then like this MPC method is at the core of our method. And we can do this MPC at each time step. And at each time step, we basically get an action target. And then after this procedure, we basically turn a kinematic trajectories into a trajectory of action labels. And these action labels, and because this all is done by in simulation, we can also do some more robustified procedures, which says we want the action labels, we give a candidate set of action labels. And on top of that, we are also going to randomize the physical properties. And we are going to search for action label sequence so that it can be robust for each kind of domain variations for the simulator. And by all these procedures, we finally get action label that it can be robust in terms of small variations in physics or small perception noises. I'm going to show this. So this is what we have in the real world. So in each corner of the videos, you see the human demonstrations. They are either given mocap labels, so it's just our vision pipeline, so that we can get the 3D trajectories, and it's able to finish different tasks by just doing replay of these action trajectories. And the reason we just do open loop replay, I mean, there are several reasons, but the main motivation is to show the action trajectories is dynamically feasible, and you can directly use it to collect the data or execute the policies in the real world. And of course, this does not give as robust policy. As robust the results as a real world perceptive policy. And in a very recent work, we are trying to extend this work by trying to add another step of RL training. That is, follow similarly, we are going to do the retargeting, but using this retargeting as a reference trajectories to guide the RL policy RL policy learning. And finally, deploy this RL policy in the real world. And we basically show this framework can be generalized to different tasks and different robots. So including scissors, screwdrivers, or using either leap hand or Wuji hand. And it can also generalize to initial configurations if we just do properly randomizations in the real world. So for different configuration of scissors, you can successfully pick it up and then doing this using scissors motion. And similarly to the screw driving task. Okay, and the takeaway of this is we can use simulation as a tool for retargeting. And these retarget trajectories are executable and can be reliably replayed in the real world or used as a supervision. So this is a combination considered combining like human data as well as sim-to-real. They can actually benefit each of the field. So from the sim-to-real perspective, this provides a natural reward signal so that you do not need to design the reward task by task. From the human data perspective, this basically makes your human kinematic trajectories dynamically feasible, and so that you can turn a massive amount of data to be valuable robot action trajectories. And my final work, I'm going to probably speed it up. I guess I don't have too much time, is there's no forceful interactions when learning from human videos. And so we developed this open source tactile glove to trying to solve this problem. And the idea is that if in the human data collection, there's a human wearing some glove, and this glove captures the tactile signals during manipulation. And if we can put the glove directly on the robot during deployment, then the visual gap and tactile signal gaps will be much reduced. And this is our goal of this project, but of course, there are some other things need to be discussed before we achieve that. For example, I'm going to start by introducing this Osmo glove, some characteristics of that. So if we want to have this glove, there are several requirements that it should not constrain human dexterities. So you must have wear some more complicated, or although accurate, but maybe heavy gloves, so that after you wear the glove, you are more like to wear exoskeletons that you cannot do full dexterous tasks you previously can do. So when we designed this as a principle that we want this glove to be thin enough so that it does not constrain human dexterities. Other factors, including we should have better tactile sensings compared to normal force, so that we build this rich shear force sensings and cover the whole hand with that. And of course, there are also some bonus that we wanted to be compatible with in-the-world hand trackings. And ideally, we just want to put it in a similar to a same size robot hand compared to humans, so that they can directly transfer. And the underlying techniques is basically these magnetic tactile sensors. So you probably have heard of reskins or anyskins, which essentially is put some magnetic sensors on top of some surface, and then the sensors will sense the magnetic flux when there's a contact. So this is how to translate the contact signals to some other magnetic flux signals, and then we can translate that into our contact signals. And the examples of data we collected is like this. So this video shows it can really capture some fine-grained motions, and the signals will change in a meaningful pattern when we do some either periodic task or some forceful manipulation tasks. And I'm going to show some of the tasks we show the human to robot transfer. So for example, when we have this human wearing glove to collect data, we can get vision, we can get kinematic structures, we can also get the tactile signals in the real world. And then we are going to, just keep our promise that there's a human wearing glove. We can directly also put this glove on a robot hand. So this robot hand we use is the psionic hand. And you can see the visual appearance is quite similar, so that the one of the gap is kind of minimized. And by using maybe around 50 demonstrations, we are able to do this real world policy on this wiping task. Although it's simple in the current in the absolute manipulation capabilities, but it's kind of a promising signal that we can do this. We can have these hardwares and do this task and transfer easily to the real world. So to summary, we have contributed this open source tactile glove so that we can minimize the visual and tactile gap. So this is basically is also compatible with existing human to robot pipeline. So next time, if you want to have human collect data, you can put this glove on your human operators so that you can get more signals and hopefully better results for your policy. And with that, I'll end here, probably a little bit over time, but I'm happy to take any questions.
Does anyone have questions? Okay.
For the part about the using the physics simulator to validate potential multiple actions and select a good one, is that something you can do in real time, or is this sort of done offline and then you know you have the right action for that situation?
Yes, that's a great question. So in that paper, it's not real time. So it's basically we already have a trajectory like from human data. And then our goal is to put that whole trajectories put into simulator and convert it to a better trajectories in terms of physical plausibilities. And this process is maybe, I think, 10 times slower than real time, but because it requires sampling a lot of actions at each time step. But for comparison, previously, these procedures may require hours or days to turn one trajectories into physically plausible trajectories.
Hi, everyone, and thank you for attending. My talk is entitled Embodied Intelligence from Human Experience. So I think everyone in this room knows robotics is very hard. I think I've spent, basically much of the past 4 years trying to get robots to do things that I've been able to do since I was 4 years old. And what I think this does when you reflect on it is it makes you think about how incredible humans are. When you watch videos of humans and side by side, humans generalize to such to things that we would find insane in robotics, like completely new tasks. You put a person in, any kind of, room, the level of dexterity that, humans can do things is truly incredible. And so side by side, there's like a massive gap in like the generalization and dexterity between robots and humans. And I think some have even argued that the goal of AI is actually to close the gap between human and robot or computer intelligence. And so, Rich and Knight say that AI is the study of how to make computers do things at which, at the moment, people are better. So this might be daunting, but I think a cool framing is that humans actually have all the knowledge that we're hoping to imbue into robots. So taking this view on how to learn from humans, I think it sort of is a promising approach. And so, and I think this is sort of a common theme that we see in a lot of domains. So, I think a common sort of framework for a successful AI system now is it actually begins with pre-training on vast amounts of human knowledge. So in the context of LLMs, this is internet's worth of text, and for vision, it's billions of captioned images that have been uploaded to the internet. And an enticing option in robotics has maybe been this ever-growing corpus of human video of people actually in the real world performing real labor. And the question, of course, is how? How are we going to leverage this data? So I think the first part of what I want to highlight in this talk is the initial methods that we've developed, over the past couple of years to actually leverage human data. And so that's going to bring us straight into this first work from about a year and a half ago titled Ego Mimic, where we really started to look at some initial recipes to leverage human data. And so Ego Mimic was, definitely not the first work to look into learning from human videos. But at the time, before Ego Mimic, most people who were learning from human videos used videos like this, where the state you had was basically an image. And so because the sense, like the modalities that you have in this are mostly just visual, people designed a lot of different proxy objectives towards actually like leveraging and training with this data. So for instance, people use things like motion tracks, they use it for like self-supervised vision objectives. They use it for reward modeling, and they used it for hierarchical policies. But in Ego Mimic, we felt that all these were inherently limiting because they were using some sort of proxy metric for what we actually care about. And what we actually care about in robotics is producing like low-level control actions. So in Ego Mimic, we kind of thought of a new form of human data. Because we didn't want to use any form of proxy objective, we considered what we call embodied human data. And so this is a little bit different. Instead of just being the state just being an image, now the state is an image as well as hand positions. And you can, using these hand positions, you can construct actions in the same way that you do in a robot data set. So this can be like the future hand positions projected onto the current frame that you're at. So with that framing, the goal of Ego Mimic is really how can we collect and learn from embodied human data? And so I think we were lucky because thanks to like simultaneous advances in different kind of XR technologies, we found that headsets like these Aria glasses were sort of the perfect tool to capture this data. So not only does it capture like a front-facing RGB view like you would have in a robot, but it also captures some form of actions, which is this like highly accurate hand tracks. But to make this data useful, we needed to bridge some gaps between human and robot. So this started, so basically kind of digging into what we did in Ego Mimic, we on a hardware side, we set up this like this low-cost humanoid robot by mounting these Aloha arms upside down in more of a humanoid fashion. And we also aligned the visual sensors between human and robot, leveraging these Aria glasses on both. And as a result, you can see on the left that the data that we captured from humans is really closely matching the data that's coming out of the robot. And this enabled us to have just very simple co-training recipes for Ego Mimic. So digging into like how Ego Mimic works, basically at a high level, our algorithm is just co-training on human and robot data. So we basically take in visual observations from both. We take in a state, which is a hand position or robot pose, and we individually normalize these proprioceptive values. Both are processed, like both domains are processed by an entirely shared vision encoder and an entirely shared policy network. And for our first attempt at like the action prediction, what we did was we used joint value prediction for all our robot data. And we had a shared head for 3D pose prediction because 3D pose is well defined for both human hands as well as robots. And so with this recipe, we evaluated on a number of challenging real world tasks. We did a bunch of things like folding clothes and bagging groceries, and we saw strong co-training performance doing this. So to kind of dig into like the comparisons we did, we compared like to ACT, which was trained on no human data, versus Ego Mimic that was trained with a couple hours of human data, and we were able to see like large co-training performances for an in-distribution task. And in addition to ACT, we also compared to a work called Mimicplay, which was one of the state-of-the-art methods for leveraging human video at the time. And I'll actually dig into this because I think it reveals something interesting about the problem. So the way Mimicplay works is that it uses human data for this high-level planner. And this high-level planner is then used to basically modulate the low-level control. And the low-level control is trained on only robot data. So I think the important observation here is that there's no gradient flow from human video data into the low-level control. In contrast, basically every single parameter in Ego Mimic is shared between human and robot. So there is direct gradient flow from the human experience data that you're collecting onto low-level action prediction. So this kind of gets to the point that we think that direct co-training may offer more direct knowledge transfer than hierarchical policies. And so, as a result, we were able to see that, our policy was able to generalize to a sort of an initial form of, we saw like some initial signs of generalization where we could take our robot to new scenes and on like new color objects, for instance. And so then the second part of this talk is actually about studying the nature of transfer. We wanted to understand like what actually allows you to get more out of human data, what drives transfer. And so this actually came from an observation right at the end of us studying Ego Mimic, where we started to look at these t-SNE visualizations of the human and robot embeddings between our new Ego Mimic policy and some prior work like Mimicplay. And what we found was that Ego Mimic was doing not a perfect job, but definitely a better job at having overlap in latent space. And we kind of hypothesized that this was like a favorable attribute of a model that you would train. That a model that was going to share a lot between human and robot, we hypothesized would have good overlap in latent space. And so this kind of let us ask two questions. should we induce latent overlap manually? And then can it occur naturally? And this actually kind of basically were the motivating questions for two of the following works. So one was like on how to induce latent overlap manually. And so this work was led by my awesome co-author, Ryan Benamia. And basically Ryan was asking this question, hey, these have really low overlap, and this doesn't make sense to me. So he designed a method to more directly induce overlap in latent space to push transfer. And so he framed this as an optimal transport problem. And so if you don't know, like optimal transport is basically a way to find the least costly way to move probability mass between a source and target distribution. And in this case, these distributions are latents between human and robot data. And so in order to use optimal transport, basically you need to define two things. You need to define a cost matrix, which is basically the pairwise cost to move points in space, and then a distance function. And so in the case of in what we did in EgoBridge was our cost matrix was based off of like the dynamic time warping distance between the trajectories of human and robot to basically characterize how similar those shapes were. And then the distance function was basically an altitude feature distance. And so once you optimize this via our optimal transport loss, we basically induced human and robot distributions to map similar trajectories between human and robot into a similar latent space. And so we can see this directly where by training with EgoBridge, we have far more overlap in latent space. And we even found that some of the latent embeddings had pretty semantically meaningful overlap, where you can see in both of these you have like the robot and human hand using their left hand grabbing something on the top right of the table. And so then the follow-up to this was actually, can it occur naturally? And this is work that I explored over at my time at Pi, where we tried to study what allowed for emergent human to robot transfer. So for context, it's just a recap. We were building off of works like EgoMimic, which had small single task policies. They relied on some form of visual alignment. They had not huge forms of generalization, just like to a new color item, for instance, and still imperfect latent alignment. And so, sorry. Sorry, just 1 second. Okay, there we go. So in this work, we were basically trying to study human to robot transfer in the context of strong generalist VLAs. And what we found was that actually very simple co-training recipes enabled object, scene, and task level generalization without explicit alignment. So the setting for this work was basically that we collected human data across new homes, spanning new objects and tasks, and we fine-tuned π₀.₇ with it. And we used basically the standard fine-tuning recipe that was used for all different robot embodiments. And we evaluated on these new concepts that we collected this human data for. And so what was exciting is that across the entire suite of tasks that we tested, there is a very clear improvement by post-training with human data. So in this graph, you're basically seeing that in these generalization tasks, which were like busing new items, basically cleaning in a completely unseen kitchen or bedroom, and this new task of sorting eggs by color. All of these tasks were never seen in robot data, but by post-training with human data, we're seeing very clear performance improvements by basically just this very simple co-training recipe. All we're doing is treating the human as a robot, and we're co-training. So this leads the question. Oh, sorry. Actually, to kind of just highlight some of these results, like we were able to additionally train like a robot to sort this toolbox, where it learned to put like the large items on the bottom and the small ones on top. It learned to tidy this completely unseen bedrooms, like placing all these items into specific parts, like basically specific compartments that the user specifies, and to sort produce in this unseen kitchen, where like the bananas go on top and then the limes go on the bottom. So the real question, and kind of just like drawing back to so much from before, is like we're asking like what actually made this work. And so we were able to design a study, and it turns out that this transfer emerged with diverse VLA pre-training. So I'd like to just explain this experiment to you guys. basically what we're doing here is we're comparing two things. We're comparing a pre-trained model's checkpoint. So basically like a π₀.₇ style pre-training, which has only seen a bunch of robot data across the Pi corpus, and a checkpoint where we post-train that with human data for these new concepts. And so the only thing we're going to be varying is the strength of the pre-trained model. We'll take models with zero pre-training, so very weak, all the way up to the like π₀.₇, which was like the strongest model at that time. And we're then going to evaluate on that same suite of generalization tasks. And so the question is, does the improvement from human data scale as the pre-trained model gets stronger? So here what we'll do is we're going to plot success rate as a function of the pre-training diversity. And so like I was saying that in blue, we're going to have the pre-trained model's performance, and in yellow, we have the performance after post-training with human data. And so what's really fascinating is that early on, we're getting very little lift at all from human data. But as the pre-trained model is trained on more and more diverse data, it's just what naturally enables this transfer. And so what you can see in that last point, that is the where we're seeing the strongest lift. That is using the full π₀.₇ mix, which is seeing all the data up until that point, including in data from many different embodiments. So the difference between those last two takes is really highlighting how training with cross-embodiment data at pre-training enables you to generalize from human data. And it's kind of just like leaning into this hypothesis that if you really consider human to be just one more embodiment, that you want to cover a wide range of embodiments to learn from it. And so then digging in even more, so that I think that kind of highlighted what enabled the transfer. It was diverse pre-training, but we wanted to understand what capabilities of the model and what properties of the model actually enabled this. And so kind of leaning back to this TC analysis that we've done in a lot of these works, things tied together really nicely, where what we saw was that with very little pre-training, the model fully disjointly embeds human and robot data. You can see there's no overlap in latent space, but only by training the pre-trained, only by changing the pre-trained checkpoint that we started from, we just naturally see much more overlap in latent space with the human and robot distributions overlapping a lot. So to recap, over these past few works, we had relatively little alignment, in ego and in mimic play, which was prior work, and in ego mimic, our first attempt. And then and then we kind of took two different approaches. One was the more active approach in ego bridge to achieve strong alignment, and one was the more passive approach and data-driven approach, which was basically the work that I was leading at Pi. And so I think this work made me think a lot about what kind of data and what the data mixture is going to look like for us going forward. And so I think I definitely used to subscribe to some idea of this data pyramid, where basically where web data kind of serves as the foundation, where you have which is most plentiful, and then you're going to have some small amount of robot teleop data. And while I agree with these quantities, what I don't agree with is sort of the structure here, which sort of implies that web data is the foundation to leverage everything else. I think what this work was kind of showing is that it's a little bit of the opposite. I think it's actually having a really diverse base of teleop data that enables you to learn from these more free-form sources of data. And in a way that this diverse teleop data sort of serves as a bridge to be able to leverage diverse sources. And so maybe we can talk a little bit about what I think kind of what actually first we can kind of recap what our current data distributions especially at the in the context of this my internship work, where basically we had a pretty wide distribution of robot teleop data, but it is kind of sparse. It is not feasible to collect robot teleop data for every scenario you could ever think of. You basically are collecting episodic data. So you pick n tasks that you want to collect, and can be super large. But then you're going to collect a bunch of data for each of those. So that's why we have these sort of spiky distribution here. And then episodic human data looks something like this, where for those same kind of enumerated tasks or some new generalization tasks, you also collect additional episodes on top of that. And so this is kind of an example of a task where you have paired human and robot data. And this might be an example of those generalization tasks that I was collecting for. And so I think the kind of obvious thing that was missing to me when after thinking about this is that so this sort of makes sense for how you want to collect episodic human data. But really what we're interested in learning from in the long run is is more freeform, long horizon human data. And so what I think what we really want is basically this sort of very, very wide distributional coverage of long horizon human data to help us fill in all the gaps between the kind of places that we're collecting more structured data collection, like episodic teleapp data. And so this is what really led basically me and Ryan and a lot of people from Danfei's lab, as well as many labs, to start thinking about a new egocentric data set. So this brings us to our work, Egoverse, which I co-led with Ryan, who is also here, so you should check him out as well. And so Egoverse, so I think that when we're thinking about Egoverse, the question is like, why do we need another egocentric data set? There's already a ton out there, and I think the real issue is that most of these egocentric data sets that existed were also just like human video. It wasn't the embodied human data that we've been talking about with more rich sensorization. And the data sets used in works that were using embodied human data were basically very small, fragmented across labs, and difficult to extend. So we had a few guiding principles when we wanted to develop Egoverse. We wanted to collect embodied human data tailored specifically for robot learning. We didn't want this to be another data set that could be useful for robotics. We wanted to show on day one that it was useful. We wanted reproducible baselines across multiple institutions to instill trust that this is not just something that is not reproducible, that only one person can do, that anyone can use this. We wanted to balance the difficulty between doing controlled scientific experiments as well as having enough data to scale. And we wanted it to be extensible. We wanted anyone who is part of the egocentric community to be able to contribute data here. So now I'm super excited to present Egoverse. Egoverse is kind of can be thought of in three components. And first, basically, we'll talk about the data set itself. So in the data set, you see two main splits. One is called the flagship split. The flagship split is meant to be thought of as that episodic style human data I was talking about before, where we collect data for specifically enumerated tasks. So we pick these 6 flagship tasks that we collected across all 4 of these institutes for hundreds of demos. And when you zoom in close to one, when you zoom in close to one, you can see that it really resembles what a robot teleoperation data set would look like, except it's just with people. In contrast, that kind of data alone was not, it's sort of not enough that we want to scale. We also want some much more free-form data to cover the long tail and the millions of tasks that happen out in the real world. And so with this, we partnered with companies like Mecha and Scale AI to go and collect data out in the wild. And so they through their operations networks, employed hundreds of collectors to collect 1,200 hours of data across such a wide variety of manipulation useful tasks like packing suitcases, cooking and cleaning and doing laundry. So we really wanted it to be tailored specifically to be useful for robotics. And all of this data is annotated. So you can see that data in Egoverse basically has rich 3D hand and head tracking, and it has dense language annotation, which is becoming a standard now to training state-of-the-art VLAs. So then second, we can talk about the study we did. The first experiment that we really wanted to validate is whether we could replicate these ego-mimic style code training performances across many different labs. So not just us at Georgia Tech, but across many institutions. And so what we see is that basically we were able to replicate performance improvement on these 3 tasks, but also across 3 different robots. And so all using the same exact recipe, code base, etc. We were all seeing very consistent performance improvements, especially on these out-of-distribution tasks. Then it led us to ask what data mixtures are most effective for co-training. And I think we observed a really interesting trend. This is just zooming in on one of the tasks we did. You can see that basically when you co-train on these 2 bars, which is basically robot data plus Egoverse data, or robot data plus just aligned human data, there's a very modest improvement. But But the large improvement comes when you leverage both aligned and freeform data together. And what this is really highlighting is that some amount of aligned in-domain data is sort of an anchor to leverage more diverse data. And so kind of zooming into this data picture again, what it's saying is that you need this aligned data where there's both teleop as well as episodic human data in order to be able to leverage this more free-form, long horizon human data. Now, finally, we can talk about the collaboration. Sorry, there we go. Okay. All right. So basically, we built a lot of infrastructure to support Egoverse, and it allows for people with heterogeneous data sources, whether it be human data from RDA glasses or another custom rig, or in-lab robot teleop data. And that all gets uploaded to a unified cloud processing pipeline. So data gets uploaded and it automatically kicks off these like ray-based parallel processing jobs to go in and process the data into a training-ready format, as well as log it into a SQL table for anyone to query. And then all of this data is viewable on a web dashboard. And then in addition, when you're ready for training, you can specify whatever filters you want. It'll pull from a cloud storage, and then it will put this data onto your local machine so that you can train on whatever cluster you want. And so kind of just zooming in to see how a user might use this dashboard, someone could go and select a lab and a specific task that you want to train on. You could go and click on a specific episode to view, and then you can go and watch that episode. And what's exciting is that we're really open for collaboration, and we've already seen, an incredible amount of reach out from the community, and we're looking to just continue growing this Egoverse effort. And we're super excited that, in addition to the two initial partners that joined us, Mecca and Scale, we have 3 new companies joining now to try to get us to our milestone of 10,000 hours. And yeah, with that, I'll conclude Egoverse and actually my entire talk. So thank you guys for listening. And I'm happy to answer any questions.
Oh, hello. Yeah. I guess I'll just repeat the question if people didn't hear. So basically, the question is like we both have approaches for to align human and robot data via explicit alignment objectives, and we also have maybe some more data-driven approaches to just have the model naturally learn such embeddings. And I think the answer here is perhaps unsatisfying. I think probably we're going to see some combination of this, and whether or not there's actually a lot of instantiations of the form of designing some objective to produce better alignment. Like in EgoBridge is a very explicit form of alignment where you're trying to directly pull together latent there's direct objectives on the representations. But there's a lot of forms of this too. For instance, I would argue that the way that you set up your action prediction to be aligned between two sources is another form of explicitly aligning. Right. And whether you target your hand data before predicting is also a form of alignment. And so I think there's definitely going to be some combination here where the way that you actually set up your learning objective will impact how your latents are distributed. And maybe not exactly in the way that we did it in EgoBridge, but maybe in a slightly more extensible version of it where maybe there's useful biases to inject
like two trajectories that cover similar language might want to be embedded into each other with similarly to each other, kind of like an eclipse style objective. And so I think we want to be thinking about both of these. But the data-driven approach is sort of something that will kind of I just wanted to highlight that this will sort of happen naturally. And it's not really about, I think, like some magic point between the 0 and 100%. It's like a relatively smooth movement over, over that slider. And but the thing from that part that I really want to highlight is the importance of cross embodiment data. So I think you can see that, especially on that performance improvement chart, the performance was improving, but somewhat modestly. And the real big spike comes from including a lot of cross embodiment data. And my real hypothesis here is that it's basically that when you're trying to learn from an n+1 time embodiment, that's much easier when n is large. Yeah, I think it's like maybe like a necessary but not sufficient condition. Where like if you're not seeing overlap, you can kind of directly probe into the model, and you're seeing that something is happening in your learning objective that's causing the model to decide that it should think about these things differently. But I'll say there's definitely nuance here, and I mostly use it as an interpretability angle. Like for instance, like the way that you generate those embeddings, like which exact layer you're going to pull from, which tokens you're pulling from, will completely change. How that looks. So it's possible that you could get something inconclusive. So I mostly think of it as an explanatory tool. Thanks. Yeah, the question was on what do we need to think about for pre-training with large amounts of human data. I think it's kind of exactly what I'm working on every day now. And I kind of decompose this into two parts, I would say. I think the first part is basically I think the decomposition is between the fitability of human data as well as the transferability of human data. So on the fitability angle, I really prefer to think of human data as if it was another robot embodiment, and I think we should be able to observe the right kind of scaling laws on it. And so what we should be able to see is that we should be able to see trends where on the human data that we are choosing to use in our mix, that you should be able to really accurately predict what the person is going to do next. Like this first part of the problem is really like we are trying to behavior clone a human, and we need to be able to have an accurate predictor in all sorts of scenarios on what this person is going to do next. So you can kind of think like, instead of training a generalist robot, you need to be able to predict in any scenario where there's a person and a language command, you should be able to predict exactly how their hands are going to move next. And this might be via some video modeling objective. This might be via low-level action prediction. And then the second part of this is the transferability. And this is actually sort of a disjoint problem, because like once you have such an accurate human predictor, now you can also in parallel solve the problem of how do those actions transfer to the robot. And I think this is where things like exactly how you represent your actions is going to matter a lot. I think a lot of the work that is being done on retargeting and functional retargeting is going to be super important here. I think this is where the sim was going to play a bigger role. And I think I think it's basically the decomposition between these things. You need to be able to copy what a human would do, and then you need to be able to transfer that onto a robot. Yes. Yes, it's a great question. The question is on how further we might want to consider sensorizing humans. And I think there's a really important nuance here. So I think I'm trying to sell human data as another form of robot data, but there's one really, I think, important fundamental mismatch. And that's in human data, what we're calling action is actually state. So the action, which is future hand positions, is actually the measured state of where the hand currently is. And this is different from robot data, where you have a commanded action and a controller gap and a state. And so in order to, I think kind of to fill this missing gap is kind of where tactile data is very important. Because when you're observing a person grabbing something from egocentric video, even if you have the state of their hand, it's very difficult to estimate how hard they're grabbing it. And so I think this is part of where where tactile is sort of I don't even think of it as just another modality. I think of it as potentially a necessary proxy to model the human's action rather than just the state that they're in.
Right. Thank you.
Thanks, Simar, for your wonderful talk. And let's continue. And our fourth and last speaker is Wenlong Huang, and he's also joining us online. Wenlong is a PhD student at Stanford, advised by Fei Li, and his work sits between robot manipulation, foundation models, and 3D vision. And he did his bachelor at UC Berkeley, and he has also won a lot of best paper awards. And he's within us remotely. And Wenlong, can you hear us right?
All right. Hi everyone. Thanks for being here. Unfortunately, I'm not able to join in person, but I'm still very happy to be here to discuss potentially a different angle for scaling robot data, because this is a workshop about data-centric robotics. So and the proposal here is maybe we can scale robotics with counterfactuals, and I'll expand what I mean by here. So first of all, the motivation I think is very clear that we've been really trying to train really hard on the quest for open world robots. I think everyone is trying to do that. This is a slide from a couple months ago, but obviously it's all outdated for all of the videos here as of today, right? So, but I think looking back in the past few years, we've really made tremendous progress that really drove all of these capabilities. I think notably we have on the algorithmic side a more expressive class of architectures, including diffusion policies and architectures derived from VLMs and more recently from world models as well, but also from more affordable hardwares. And you can literally buy a robot for $200+ today. And a lot of classes actually already using this type of robot. So it's really democratized, like we can have the robots everywhere. And it's really been the consensus that as long as we can demonstrate some behavior, then we can have a policy to learn it. And so there's this video that I really wanted to show. So this is like a recent, I think a couple months ago, this is a video from physical intelligence, which is super cool. This is like a task where the robot is doing this autonomously. So the task is flipping the sock inside out. So this is not a multi-finger hand robot, obviously. So this is just jaw gripper, parallel jaw gripper. And what the robot is doing here is literally like you kind of wrap the sock on one of your grippers, and then you can do a pinch grasp from the inside of the sock and then pull it out. So this is amazing, right? I mean, this is obviously like a really cool task to me. And then I think important. I mean, of course, this is taught by humans in post training, and I think it's also very cool to me in the sense that this is obviously some insanely hard thing to reason in language. I mean, in order to tell you this, I'm not able to just like write you as write the sequential number of steps, 1, 2, 3, 4. That's what you do. I need to show this video, and then to me, this is very cool in the sense that I've never seen this in my life. I mean, like not only for human or for a robot, I don't even know if this is how you can flip a sock inside out. So what this means is that this is not something in my pre-training data or in my post-training data. But somehow, as humans, we have the ingenuity to be able to do it. But why? Like, where does that come from? There's clearly a gap where maybe the robots will never have in their data, whether it's from their own data or from other source of data, internet scale data, or any other source of data. So what this comes down to is really a capability to acquire novel behaviors autonomously. Obviously, this is some capability that we want to replicate that humans obviously have, but robots don't have. And the key proposal here is that there has to be a way to think about counterfactuals in order to have this capability. And what I mean by counterfactuals is that assuming you have a nominal trajectory for doing some task, and there needs to be a way to think about or evaluate the result of taking a slightly different action. But not only slightly different, it needs to be, what if I take a very different action? Can we have a way to tell us what's going to happen under that situation? And this is really the driving force, in my opinion, behind many of the big AI breakthroughs in the past, right? Like if we look at AlphaGo, this is the move 37. This is a move that no human has ever done in history or in any of the gameplay, but the AI figured out itself that this is the right way to play. And it's not only that, but also deployed systems today, right? Like Cloud Code and Codex, etc. If you look at literally, like there's always a reasoning effort on how hard you want the AI to think about the counterfactuals. And this is very important because uh, I mean, I'm not on an unlimited subscription, right? I mean, there's always a budget, but I also set it to an extra high because that does tend to produce better performance than lower reasoning effort. And I think Noel Brown also has this wonderful slide where he was showing that basically, if you look at Go, all the results that people have published, they all have some sort of way to do reasoning or search in it. So if you remove that search, then this is the gray line, and it's so much worse than the human performance. And I think the people also publish so maybe from the AlphaGo paper, people they also published this result of that if you remove the search, you need to scale your data by 100,000x to get to the same performance. And this is removing the search at test time. If you remove it from training time, the number will be astronomical. So if we have any reason to believe that robotics is harder than coding and Go, and we actually really have every reason to believe it is the case, then this counterfactual reasoning capability has to be there somehow. So we can discuss like okay, so if this is the capability that we want to have, then what should be the space of counterfactuals to think about? Well, first of all, since we have all this amazing system today, coding system, like it's very natural and tempting to think as of today, 2026, that maybe this we can just do language or code-based reasoning because that works. And yes, it does work. And then this is exactly what we tried almost 5 years ago. So this was like June 2021, 5 years ago from now. But then it was also a year and a half before ChatGPT was released. We were looking at how we can use language model to kind of decompose the task in this like really toy environment. This is pure language-based environment. There is no grounding, no robots. This is not even a robotics paper to me. Like it's more like testing this hypothesis whether language can be used to think about the tasks. And surprisingly, without any training, it actually works. So for coming up with the sequence of steps to do some this like interesting thing that I mean people typically do, and then later folks at Google also put this on a real robot. This is the SAIL work, and then they also introduce a way to ground this with value functions. And this is also the time where reasoning in text and language really kind of starting to kind of blossom, right? Like within the robotics and also outside the robotics. I'm also involved in quite some of the works during that time, like Intermodal, POM-E, Codex policy, etc. However, one thing that's obviously challenging here is that you cannot really ground this language. I mean, this is still in really abstract space, so we need to somehow ground it in a space that robot can understand. So this is some follow-up works that we did where we grounded two potential maps with Vox Poster. This is the paper, and then we had some of the results where you don't need any demonstration data, and you can do some like simple pick and place style tasks on the tabletop environment. And then later we also had an extension called recap that grounds this, still doing the reasoning in language and in code space. But then if you have a way to tell the VLM, this is the point that you can reason about, then it can tell you, okay, maybe I can construct some of the code-based constraints that can say, okay, if I want to pour a tea or something like that, I can construct the constraints that connects different key points in the scene, and then we can solve it with constraint optimization to get some of the behaviors. This is, I think it's already 3 years ago or something, but all of this are achieved without demonstration and really something that the robots are acquiring for the new behaviors at test time. But I want to come back to this example, right? Because obviously all of those tasks I've shown, right? All of those are easier in terms of how you can use language to reason about it, or with the help of some way to point to or do some visual prompting in the scene with like key point, etc. However, if you give me this task as a sort of quote unquote Oracle language model myself, right? As a person, I don't even know how to even start describing how I can do this task in language or in code. So I try to feed this to ChatGPT, and then this is what I got for how to do this task. The robot begins with a sock lying approximately flat on the table. The opening is accessible, and both grippers are approached from above. Okay, I'm not even gonna read all of this, but obviously you can see that this is like really absurd, and we can't even. It's not really possible to think about this and reason about this in the space of language. So counterfactual reasoning in language space is definitely useful, but there is a clear ceiling. And where is that ceiling, right? So if that's not the space, then what should be the space to think about counterfactuals for robots? And obviously, there needs to be a way to think about this in the lowest level of actions, because that's the lower level you can think about this, the more room you can do the improvement or to come up with the novel strategies. But what is really an action, right? So there's all these different robots out there, and then there's all this type of grippers out there. The same gripper can also have like different length, different width, and I can have different number of fingers. I can have like even different deformation, etc. So it's really hard to think about whether there is a how we can get to a unified low-level action space. And then it doesn't even sometimes it's not even one robot or two robot arms. It could be like three robot arms. Try manual manipulation, why not, right? So that's really cool. But then how do we think about a unified action space to think about the counterfactuals? Because we always definitely want to build a general purpose model to be able to do that. So to me, I think actions are best to be thinking about in the space of 3D in terms of the robot's geometry. For example, here are some different ways to tidy up a robot, but whenever I'm doing that myself, I'm always looking at the robot I'm controlling, and then think about how it's moving in 3D. For example, I can reach to behind a box. I'm not even able to see it in my view, but I can still know where that robot is in 3D. So this is the work that we recently did called Point World, scaling 3D world models for in the wild robot manipulation. And the idea there is that given a RGBD capture, it could be one, it could be multiple, and then we also are given a low-level action space that's specified by the robot's description file, typically the URDF, and the low-level joint space robot actions. So all of these are input, and the output is how can we simulate the whole scene of how it evolves under that action space. And the action space here is the 3D flow, because this is something we can sample from the robot URDF. It's also embodiment agnostic to the agnostic to the kinematic structure, the hand geometry, and the number of hands. And what we do is that we just sample endpoints from each link, compute the forward kinematics, transform the points for each link. And then because the scene observation is also RGBD, so we can unify the state representation and the action representation both as 3D point flows. So the input output is quite simple. Basically, you have an observation of the scene in terms RGBD with point cloud at step 0, and then you have also analytically computed robot 3D point flows given known robot model, and then the output will be how the scene will evolve under that perturbation. So we train a model to effectively be a zero-shot real-world simulator for robots. Basically, given all of this, the architecture is simply just a transformer, and the output is a full scene, 3D scene flows on how that scene evolves. For example, here, this is a deformable object. And there's really many like unseen rollouts we can do with a single pre-trained model. So all of these are on the website. I'm only going to show a couple of them. So here, this is the one that I was showing previously. So this is the deformable object. You can see that the cloth is really deforming in a way that's realistic. And there's no object segmentation. It's really simulating the whole scene. And here, this is a robot in front of a fridge. It's trying to move forward, and then the model needs to predict if the robot does that, what exactly will happen to the scene. So here it needs to implicitly identify the kinematic structure of the articulation structure of the fridge under that action. And then here's another interesting one where with the egocentric input, you're now able to see the back of the box. So it's actually empty from the other side. And then, but what's interesting is that because the actions are always fully observed, because they're sampled from the robot URDF, you can see that how the model needs to implicitly reason about the contact geometry and then the events to predict how the box will be moved if the robot's lifting up the box like that. And here is another scene from, I think here it's robots holding a box, a bowl, and then there's an object in that bowl. And then in order to predict what's going to happen for the entire scene, it needs to reason about not only robot-object dynamics, but also object-object dynamics and how everything will evolve under effect of gravity. So I think this is particularly exciting now because there has been a lot of advances in the 3D vision community that has really advances the field of 3D vision, and then we have we can really leverage that in robotics. And so what we did is that we leverage all those fancy 3D vision models, and turns out that we can label droid with like more than 60% of the scene with almost simulation level depth and camera poses. So all of this have been open sourced online. So even if you're not working in particular 3D world model or dynamics model, for robots, this is also something you can use if you're into using 3D data for your applications. And here's some of the visualization on what the scene looks like before and after. So you can see how clear the 3D point cloud are. And then in total, we have about 500 hours of accurate 3D interaction data from both the real world and also the in simulation combined total. So once we have this data, we can look into how we can scale up 3D world models such that we can have a really faithful kind of the counterfactual engine to answer the different queries. So we summarize the roadmap of what's important here. It's really coming down to like modernizing the backbone, just doing some tuning with the training objective, adding pre-trained image features and scaling up the model, which helps actually the most. And then we also have a lot of detailed discussion about specifically the trade-off of different backbones, the action representations, the generalization across within the domain, in both zero-shot and fine-tuned way. And then, of course, scaling the data and the model, action chunking, and also the effect of different cameras. So there's a lot of discussions in the paper. So please feel free to check it out if you're interested. But here I'm mostly going to show some of the application of how this can help acquire novel behaviors. So we really want to push it to the case where there's no demonstration or fine-tuning. You can, of course, do this task very easily with the current ways of doing by collecting demonstrations. But we want to push it to the hardest setting where we don't have all of this. Can it do some of the task here? And then here we're showing some of the pushing task, deformable manipulation, articulated manipulation, and some of the simple tool uses. And there's a lot of limitations, of course, and we actually have a whole page of limitations in the paper. So, and also this is something we want to call for research. And a typical comment or question I got is that this is 3D, right? Like, so 3D data is scarce. So how do we deal with it? Then actually it turns out this is a follow-up work that hasn't actually been released. But what it turns out is that what we could do is that we can leverage the pre-training with video data, just 2D data. And then with only 15 hours of data, not even 500 hours of data that we used in the previous work, we can fine-tune a video model to have even better fidelity of predicting the environment dynamics. So the way we do this here is that we take the data set that we have gathered with the 3D interaction. We get we simulate we kind of articulate the robot URDF to generate the mask trajectory and pair that with the RGB sequence, and then we can use that to train the video model. And what this turns out is that this is a model once it's trained, so it can generalize to all of this embodiment without any data at all. And this is without any additional data. So this is a single model, single set of weights, and all of these are unseen environments, unseen gripper, unseen robots. And all of these are from the single model, and you can have it to predict how the environment will evolve under all of these manipulation settings. And obviously, this can be used for doing policy eval, and we can see how well it correlates with the ground truth in the real world. So this is some of the tasks that we did. And then the gray is the ground truth, and the orange is the simulation by the model. And we can also do test time scaling by couple that with an existing policy to show how you can improve the existing policy. And this is using the robot action as the mask trajectory. But once you formulate it this way, then it's not really limited to robots because all of these are observation-only data. So who's the real agent in observation-only data? Everyone could be the agent. All the objects could be agents. And that's exactly what we did. So basically, you take a reference image, and then you ask the model, if I want the cup to be moving like that, what's going to happen? So this is purely unseen. And this is like, we literally took an image of a robot that we have in the lab. The model has already been trained. And then turns out that it can produce these trajectories to do the task. But all of this are still just in image space. So grounding them isn't easy. So you can see that clearly there's a lot of gaps in the physical fidelity currently, but it can get the rough shape correct. I think a big next step will be think about how this can be better translated to executable robot actions. So yeah, let me wrap up with some closing thoughts, and then people love to talk about the beta lesson because this is of course an area of scaling data and compute, and what typically has been talking about is the learning side, and the focus has really been trying to gather as much data as possible, and then we want to obtain really broad priors from this data. And then maybe with enough data that will generalize zero shot. And maybe in the short term, it doesn't have to be zero shot. It could be a few shot. It could be, we can have some post-training data. But that is definitely critical. But to me, that isn't the whole picture because learning, so what is really learning? Learning should also happen continuously and like throughout the entire age of the robots. So it needs to have a way to autonomously acquire new behaviors and then compile that into the existing model. And how do we get that new behaviors? We can acquire that new behaviors through the counterfactuals, through trying on different things and executing the thing that works the best. So this might indicate that there might be another way to scale towards the human level of physical interactions. So first of all, the prerequisite is that we definitely want to obtain general purpose prior about the behaviors and the dynamics. That is definitely very critical, and we should do that, and we're already doing that. I think that's great. And then after that, we need to ground them in the physical world, and then we need to go from there to acquire new behaviors with search, with counterfactuals, and potentially this could be the recursive self-improvement for robotics. This is the hype word that people have been talking about. All right, yeah, and that concludes the talk. Yeah, I'd like to thank all the collaborators and advisors, and happy to take any questions if there's any.
Okay, anyone have questions? Okay, I have a quick question, and I want to know, besides using the MPC for planning, are there other ways to utilize a 3D world model in robotics?
Yeah, so MPC is just the simplest way to do it. So what does a model provide, right? Model fundamentally provides a way to evaluate. And what I mean by evaluation here is not you can think about it in a broad sense. It doesn't have to be a fixed policy and then you evaluate it and that just gives you a success rate. If you have an autonomous way to evaluate it in the loop without actually executing in the real world, then you have an autonomous way of improving. So you can do any improvement you want if you have a way to evaluate it. If you don't have a way to evaluate it, then there's no way to improve it. So in general, World Model provides this capability. I think that's quite crucial, which is why this is the main topic of counterfactual today. I think that is something that's being overlooked right now.
Okay, thank you. And any other question? Okay, no. Thanks, Wenlong, and thanks for your wonderful talk. And now we will go on to the spotlight talks. And let me see. Okay. And now for the spotlight talks, the 3 papers were picked, and each author gets 5 minutes. They are Ambient Diffusion Policy, Human Ego, and OMG. And let's give them our full attention. And I'll bring up the first author. The first author will be Adam Wei, who will present Ambient Diffusion Policy. And Adam, you can share the screen.
Cool. Can you hear me?
Yes, we can hear you.
Okay, great. Is my screen visible?
Yes,
Okay, great.
I can see you.
Great. Okay, so today my name is Adam. I'm a PhD student working with Professor Russ Tedrick at MIT. And today I'll be presenting our recent work on ambient diffusion policy, which I think is an exciting way for to learn from suboptimal data in robotics. So I hope you guys got a chance to talk with Tommy, who was there at the poster session, and I'm sure he did a great job. But here's I guess the talk version of it. Okay, so to start, oftentimes in robotics, people will collect a small subset of like in-distribution data, very high quality data for their task. But there's also all this other data out there that might just be slightly out of distribution. And because it's slightly out of distribution, we might call it suboptimal. So this is data that comes from people like non-expert teleoperators, different robots, different tasks, simulation, and many other sources. So the goal of this talk is to understand, what are some principled algorithms for learning from these suboptimal data sources shown in blue. Okay, so before I get into it, let's do a quick overview of diffusion policy training. In diffusion policy, the goal is to train conditional denoisers at all the different noise levels indexed by some time axis t, and that's what the red axis is. And normally, people do this by training on their high quality or some robot dataset. Now what happens if I give you some suboptimal data, let's say from the internet or some like maybe human ego video, something like this? A common approach is to just do co-training and to reweight the data sets. But this is fundamentally the wrong objective because you're still teaching your policy both the good parts and the bad parts of this suboptimal data. Okay, so how can we do better? In order to understand that, I think it's first important to dig a bit deeper into how action diffusion actually works in robotics. So in our paper, after some analysis, we essentially show that robot action diffusion is actually hierarchical. So this means that at high noise levels, robots are actually learning how to do high-level planning. So in this example, we can see the robot is deciding which block to grasp, and it's also deciding which bin to put the grasp in, to put the block in. So these are all high-level decisions. Once you get to lower noise levels, you can see that the robot is really just refining its grasping motion and refining the smoothness. Okay, so we operationalize this intuition into an algorithm for learning from suboptimal data. Let's say you have data that has the correct overall plan and the correct overall strategy, but maybe it's a new teleoperator and the low-level motions are bad. Because we learn high-level planning at high noise, then it makes sense to only use this data at the higher noise levels. Now let's say you have some suboptimal data that actually has very high-quality motions, but maybe the task is out of distribution. So maybe it's the wrong pick-and-place task. Turns out you can still learn the low-level motion primitives without learning the high-level plan, which is incorrect, by restricting this data to the lower noise levels. So I should say that here we're restricting the suboptimal data usage to 2 intervals. In the paper, we provide very precise interpretations of both of these intervals, and we also provide a method for annotating these intervals automatically. Okay, let's talk about some results. So in our first set of experiments, we basically use OpenX as our suboptimal or out of distribution data. And we tested this on 2 different tasks in our lab, tower building and table cleaning. Okay, so here are the results. Here, the blue bars represent 2 variations of our algorithm, and the green bar represents the co-training baseline. We can see that in tower building, we build towers that are 33% taller than the co-training baseline, and we build towers that are 84% taller than if you had just filtered out the out-of-distribution data. In addition, on table cleaning, we explored the effect of scaling up our suboptimal data. So here, Magic Soup++ is a small subset of OpenX, and custom OXE is a much larger subset of the data. And we find that as we scale up and add more suboptimal data, Ambient actually starts performing better, whereas co-training plateaus. So these 2 results essentially show that ambient diffusion is much better at selecting out the learning from the good parts of suboptimal data and ignoring the bad parts. Another nice thing about our framework is that it's very general. And for this, I mean that it works on basically any type of distribution shift in your action space. So to show this, we tested it on 3 different types of action suboptimality, such as noisy teleop, sim to real gap, and task mismatch. And we find that when we use ambient diffusion to learn from this suboptimal data, we can consistently and considerably beat the co-training baseline. And here we've tuned the hyperparameters for both algorithms so the comparison is fair. Okay, so in summary, I presented a new algorithm for learning from suboptimal data. The key idea is to use noise-dependent data usage. We should be restricting the usage of suboptimal data to only the noise levels where this data would be beneficial. So this is actually a pretty huge project, and if you have any questions, chances are we've done an experiment on it. So I'd really encourage you to check out the paper. The QR code is on the slide. Thank you so much. And I'm happy to take questions. Oh.
Okay. Any question? Okay, no, and we will move on to the second paper. The second paper will be OMG. And Kun-Ying, can you hear me?
Can you hear me?
Okay, you can share the screen and sorry, no. Oh, okay, great. We can see your screen and you can give the talk. Over to
Okay,
you.
I'll get started. Hello, everyone. I'm Kun-Ying Lee from Tsinghua University. I'm sorry I couldn't join you in person, but I'm very glad to have the opportunity to share our work with you online today. Today, I'll present our work, OMG, Omni-Modal Motion Generation for Generalist Humanoid Control. Most humanoid controllers are either task-specific policies that require carefully designed rewards, or motion trackers that assume a reference motion is already available. Our question is, can a humanoid directly interpret diverse human intent and convert it into executable whole body motion? Let me begin with a short demo. From text, the same system responds to dinosaur, zombie, and aeroplane. From audio alone, it moves to Chopin's Scherzo No. 2. It can also follow a human reference motion. Finally, without training on this combination, it follows the text instruction, raise hands while dancing, while moving to paper rings. All these examples use one shared model. The core idea is to decouple motion generation from physical execution. OMG-DIT acts as the high-level motion generation brain. Given language, audio, a human reference, and recent robot motion history, it predicts a future unitary G1 trajectory. A pre-trained general motion tracker then serves as the low-level controller and executes this trajectory on the real robot. This hierarchy lets us scale human intent understanding without learning physical control for every modality. To train this generator, we built OMG data. We aggregate heterogeneous motion datasets, retarget them into a unified G1 motion space, add language or audio annotations where needed, simulate the motions, and filter out low-quality or physically invalid examples. The final corpus contains over 1,100 hours of robot executable motion, organized into approximately 364,000 clips, covering text, audio, and human reference conditions. On this data, we train OMG-DIT, one diffusion transformer that learns the shared prior over feasible G1 motion. Global conditions, including motion history and language, enter through cross-attention. Frame-aligned conditions, such as audio and human reference, enter through film adapters. This design is both extensible and compositional. For example, pickle control is added as an 18-dimensional frame-aligned key point signal through zero-initialized adapters, preserving the pre-trained prior at the start of adaptation. At inference time, classifier-free guidance combines modality-specific directions, enabling condition combinations that were never jointly observed during training. Across all three modalities, OMG substantially improves motion quality. Compared with strong modality-specific baselines, it reduces the main error metric by 75.6% for text, 70% for audio, and 63.4% for human reference control. Importantly, this generated motion can also be executed by the downstream tracker on the real robot. Beyond benchmark performance, the shared prior shows several foundation model-like properties. With only 1% of the target data, pre-training reduces text-to-motion FID by nearly 80% compared with training from scratch. It also consistently improves adaptation to the new pickle control interface across different data budgets. Moreover, motion quality improves as we scale the model, and text and audio can be composed zero-shot to control both semantics and rhythm. To conclude, OMG contributes three things. First, OMG data provides over 1,100 hours of unified robot executable multimodal motion. Second, OMG-DIT maps language, audio, and human reference into future motion through one shared prior. And third, this shared prior enables real-world execution, example-efficient adaptation, predictable scaling, and zero-shot composition. We believe that scaling the motion generation brain is a promising step toward generalist humanoid control. Thank you.
Okay, any question? No, okay. Because the author of the third paper, human ego is not a nine, so we'll move on to the next session. The next session will be our panel discussion, and this session will be moderated by Professor Yang Gao, who will bring up together ideas from this morning and lead us through the big open question in robot data. And we love your inputs too, so please have your question ready. And Yang.
Hey, I'm Yang. I'm a professor at Tsinghua University, and today I'm going to moderate this panel discussion session. Yeah, Simar, do you mind coming to the front? Ashwin. Oh yeah.
Simar.
Yeah. So I think we'll also have two online speakers.
Wenlong and Haozhi will be
Haozhi.
online.
Can you hear us?
Yeah, I'm here.
Yep.
Okay. Wenlong, can you hear us?
Yep.
Okay. So great. So yeah, so for this panel discussion, I would like to have probably most of the questions come from the audience. So if you have any questions, just raise your hand. So in the meantime, I also have a few questions I want to discuss with the speakers. So the first question I have is that, so this is a robot data workshop. So we have actually talked about a lot of different forms of the data. For example, the egocentric data, the operation data, and future data may be generated by the world models. So I'm wondering, what's your view on how those different forms of data will starting to intersecting with each other and converging and maybe form a unified solution towards the end? Yeah. Anyone wants to start?
Honestly, I feel like a lot of my perspective on this is actually informed by like a lot of Simar's work at Pi. But yeah, I mean, I feel like one thing we found, a lot of the work at Pi is like there's no substitute for like high quality teleoperation data. But of course, like collecting high quality teleop data, like you can only do that at so much scale. So you definitely need to be able to learn from like human data, like sensorized data flag, like unique type data, all of this kind of stuff to actually like capture like the long tail of like every possible behavior you might like ever see. And what we've observed so far is that like a lot of these like more scalable data sources, they help you like understand a lot of like high level semantic concepts, even like affordances, things like that. But we still haven't yet like unlocked a recipe that I've seen anyway from like to get like super low level dexterous behaviors out of this data. So that's where like, high quality teleop data helps close like the final.
Yeah, I think I'll add one thing to that. I think there's like a few. I think there's like two really interesting properties that have made me think a little bit differently about like the relative value of the different kinds of data. Like I think one is that I think the robustness you get out of generalizing over the embodiment axis, I think is really, really important. So I think and I think Pi was in a really good place to study this because it was naturally part of their mix to have cross-embodiment data. And I think really leaning into this, maybe in some even extreme ways, will actually really help. Like maybe like a crazy thing will be like in Sim, you can like ridiculously randomize like your controller parameters and camera angles. And I think stuff like this will actually further increase the value of more cross-embodiment data because you're effectively learning to generalize over that axis. And I think the other thing that's been changing, that's started to change my mind a little bit recently, is I think there are some modeling decisions which also change the relative value you can get out of data. And I think the biggest thing that has been changing my opinion, I think, is about seeing basically seeing like especially like Dream Zero style world models. I think that changed my opinion on basically the value you can get out of human data because it put more of the brunt of the prediction objective on predicting really good video and pixels, which I think is more transferable between embodiments. and kind of decoupled out the problem of low-level action prediction to the really high-quality teleop data you have. So I think this like modeling and data distributions are things that like sort of affect the relative usefulness of different sources.
Yeah.
Yeah, I can add something. I guess I generally very much agree about the idea of data pyramid. Like we have different layer of data sources, and different data have different advantages and disadvantages, trade-off between qualities and the cost. I think that also applies for either like typical general purpose scrapers areas or dexterous manipulation research areas. Maybe one thing on top of that for dexterous manipulation, and it's kind of also similar to humanoid research, is there are some things that we cannot teleoperate, so that we need to introduce another level of skill that is targeted. Like in humanoid research, they call it system 0, but I think it's mostly the lowest level of controller that transfer human intentions into like the more low-level dexterous behaviors. So this is, I mean, I usually consider why we can teleoperate grippers so easily is because we basically abstract the action space to be a very low dimensional action space. While for hand, we do not have that. But if we can consider dexterous hand can execute several skills, is further considered it as low dimensional actions. So maybe at that point, we can reduce the gap for teleoperating hand, and then we can get the same recipe working that works in like other type of robots to work on dexterous hand.
Yeah, so I guess I can maybe tell another perspective. I think I actually agree with everything that people have said. But one, just to add to the fun of the discussion, one claim I'm trying to make is maybe there's just no way for us to zero shot everything. Because no matter how the data, how we think about how we can scale the data, because eventually the world is really long tail and the goal can really be diverse. So we have to have some way to autonomously, like it could be we can start with simple things like adaptation. So we have the general strategy, and then have the robot do RL to do improvement. But in the long term, I really think that there needs to be a way to even come up with new strategy to do some task or adapt to really challenging dexterous tasks. So that's, I guess, like a different aspect to think about it. But I actually agree with everything people have said as well.
Yeah. So I think there's some people has a saying about the data pyramid kind of thing that you classify different type of data into like a different version of the quantity and quality trade-off. For example, simulations and human ego data might have the largest quantity because you can either collect them very cheaply or generate them for almost infinite amounts. So so people think some people think that they should be treated as the bottom layer of the data pyramid. And then comes with the, for example, UMI type of the data or any type of the wearable devices with a little bit of the close to the gap of the involvement. So and then as Wenlong said, probably in the end of the day, you couldn't do any task in a zero-shot manner. Then you can, for example, running some real-world data collection back into the loop. And I'm wondering, do you general think agree with this paradigm, or you think that maybe we don't need a pyramid, maybe just like operation can do all the work or any others? Yeah, just have some quick thoughts from you.
I'll say one thing because I think it was one of the points I was trying to make in the talk about this like inverted data pyramid was sort of to agree with the fact that these sort of the quantity of the data that we're expecting to get is kind of like naturally dependent on like the embodiment. So like I think like sort of the market forces of how easy people can collect human data at scale, we'll make it so that it's very large. And like obviously the internet is going to be even larger. So the quantity part, I think the pyramid totally gets right. I think the part
of the diversity part?
Yeah, or actually I would say like I think it's the implication on the dependence that I think I disagree with, where like it's actually different parts of this that like, for instance, like the reason that I in that example I just like kind of flipped it upside down was because without like I think one could look at that pyramid and say, oh, you need the least amount of robot teleapp data and you'll be fine because you can rely on the stuff down here. But I think that's like there's like a no free lunch where like you actually rely on having really good primitives to even be able to learn from these other sources. So I think there's a lot of reliance on different parts of the pyramid to one another, right? Yeah.
Can you elaborate a little bit more on that? So are you saying we kind of rely on the, for example, data in the for example, egocentric data to contain a lot of diverse behavior such that we can collect fewer data on the entire operation side?
Yeah, I think there's a few things. So I think the most basic thing I was trying to say was like you almost can't get anything out of the human ego data unless you have a good base of a bunch of robot-based primitives to begin with. I think that's the first kind of reliance, but there's other kinds of reliances too. Like I think increasingly I'm finding that having some pockets of your data that are really tightly aligned between like your human data and the robot data actually kind of creates these like it lets the model learn an invariance where it says, oh, I've now seen an example of human picking up an orange with the left hand and robot picking up an orange with the left hand, and having that correspondence I think allows it to interpolate in regions where there's only human data and not robot data. And so I think what I'm trying to push back on is like I think it's not just about the data pyramid, which is just like kind of quantities of data that you need for things. It's a lot about the relationship between the data, like there being matching components, or you at least having a base of one thing to be able to leverage the other. I think it's like very it's more like interconnected. Like the different data sources rely on one another to be able to be effective even.
Yeah, that's a very good point. Any other comments?
Yeah, I mean, yeah, definitely agree with Simar that like I've also found that like global data composition like matters a lot, and like you can kind of exploit different properties of these different points on this data pyramid to like cover gaps that would be difficult in other cases, right? So like I feel like especially in robot data, unless you're very careful, there's like just random data islands all over the place, right? Well, on the internet, like you don't really have this problem, right? There is kind of like a smooth continuous spectrum, like every possible thing someone would possibly think about anything, right? But in robot data, like, you know, unless you're very careful, it's like if you're trying to just optimize for like high throughput data collection, right? You'll just collect like a bunch of data on a very fixed embodiment for the same task. So like the way that you operationalize things is very different at different points of the pyramid based on like what is easy to optimize for. So for example, like for human data, like it makes sense to really optimize for like diversity across like every possible axis, because that's like much harder to achieve with robot data, even though you need the robot data to actually get like that last one. So.
Cool. Okay. Good. Okay. Let's see question from the audience.
I was curious to get all the panelists' intuition when thinking about like constructing these data pipelines for large-scale robot learning. Like, where do you see the role of each type of data, sim, ego, or real, and like where like certain like one of those might excel and like serve the need versus where you just really need a high quality trial data? Like, just curious to get your sort of intuition across those categories.
Yeah, I think Ashwin like nailed the hit this point really well. Where like today with our recipes, it definitely seems like you want to have these like these motor primitives, and what motor primitive means now is a lot more like kind of fuzzy because they're all in these learned models, but you want to have these motor primitives from as high quality data as possible. And so I think that's the idea of like you want to have like maybe in an ideal world I would like structure my teleop collection to have to just make sure that every basic primitive of like picking and pouring and scooping and all of those things have been covered in like a number of scenarios, so that the model kind of has access to these things. And then it's almost the job of these more diverse sources to like to compose those in context. So like given the language and the like very maybe a more unseen language and a more unseen visual observation that you haven't seen, the model can go back and say, hey, I know how to scoop and I know how to pull and whatnot, and I know the rough correspondence between when a person does something and when a robot does something, so then I can compose these primitives I have for some of these tasks.
Wenlong and Huang, do you have any comments?
Yeah, I think for now, maybe my intuition is the typical data pyramid is like we have diverse interval data as the bottom, and then add a relatively smaller amount of wearable devices or other type of data, and then tally up. But I think my intuition, I mean, the main argument I want to say is the content and the ratio of the data pyramid is also getting changing. So if I remember correctly, in the very initial early paradigm of data pyramids, the middle layer is kind of simulation data. And now, and because at that time we do not have a consensus of using wearable devices like Wumi or DexWumi to do that, but and we also do not have a lot of accurate gloves to capture human motions. But in the recent years, these devices become available, and the cost of collecting data, operation cost, is also reduced. So this type of data will also become a critical component, becoming the middle layer of this data pyramid. I imagine in the future, 2 or 3 years, there are also will be different research work or just the hardware development that might again changing the data pyramid. But I guess the general intuition is you should choose this amount of data by diversity coverage and also the quality, while not restricted on like conceptually definition of this data.
Yeah, I guess I'll add a different aspect. It'll be slightly different. So basically, I think the pyramid is definitely the great idea, but then there's one other side, which is the objective, the training objective. I think it's depending on the training objective, the pyramid will be very different. So currently, what we consider as training objective is that we have some action space. So that becomes kind of tricky if you want to learn from, let's say, non-robot data, like human data or internet data, because you need to have some way to represent the action space. And typically that would be done by extracting the human hand poses or by using some latent action representation, etc. I think that really is something that's also being discussed slightly less than the data itself. I think that could also be important because that matters. That will change the landscape quite a lot, I think.
Yeah, I'll add one point to that. Like, I think this is one thing that's actually making the job of like data set curation really hard. Where like for instance, like a lot of work that we're doing involves like talking to many different ecocentric vendors, and they're asking you what what data do you want, and like what is diverse data. And I think the opinions on this are changing constantly, which is like I think in the I think maybe I would observe, maybe I had an oversimplification with like VLAs. I think there was a lot more it was a lot more okay to have a bit more like repetitive data and like have like order of hundreds of demos for given things. And then what I'm seeing more with video models is that like if you do that, you get really catastrophic like overfitting in your and you really need to like extra optimize for not just diversity, but like you cannot oversample any regions, because then the model really collapses. And so I feel like as like, because these modeling decisions are changing a lot, it's actually really hard to curate the right data set, because it is so interdependent on those objectives you're doing. And there's kind of like these implicit assumptions, because like, yeah, like in a video modeling sense, you can almost assume that you have had access to so much more like video related data. And so like Yeah, it's making, I think, the problem of curation really hard. 'Cause I don't like defining what diversity you want is really tricky, and how your model reacts to like skewed data distributions is changing too.
Yeah, I guess I can add one quick thought there. I feel like one thing that I think about when figuring out okay, how do we think about how to collect data across all these different sources is that ideally for scalability, we could just use one objective, right? And the way we actually collect data across these different sources is only influenced by how effectively, what properties of that data collection mode we can exploit to get the axes of diversity and quality we want. But ideally, we're using the same objective to learn from all of them, right? So I think one way I think about that is for human data, for example, or even to an extent sim data, if you have good domain randomization stuff, you can really randomize environment properties in an amazing way that would be much more difficult to do operationally with robot data, right? Well, with robot data, you can sample a much broader set of highly dexterous behaviors that you cannot actually effectively cover in sim data, for example. So yeah, often I just think about what is a way to cover all the axes of diversity that best exploit that data collection mode so that globally I've covered everything I want in a way that I can learn with the same objective.
Yeah, that's a very good point. That is exploring different data collection mechanism so that you can get the best out of at least from this data collection node. Cool. Okay, let's move on to the next question.
So my question kind of boils down to, are we actually collecting the right kinds of data? My background is mechanical engineering. So, I see obviously there's a lot of vision being collected. It's very easy. And then at this conference, I'm hearing a whole lot of talk about embodiments and sort of the mechanical equivalencies of one system to another to interact with the world. But to me, at the end of the day, what matters is, the forces and shears right at the fingertip. But I don't necessarily see us collecting a lot of that kind of data. If we were to pivot to that kind of data, what do you think that would do to our ability to train machines to think in terms of just interacting with the world as opposed to trying to move and manipulate it, from one degree of separation?
Yeah, I can briefly speak to that. So I think, yeah, collecting, data with more rich modalities, force sensing, all of that would definitely be helpful. I think one challenge that we face as a community in practice is that scaling up data collect with high quality force sensing can be quite difficult. Often commodity force sensors will either be relatively unreliable, or if they are reliable, there'll be a lot of hysteresis, so you can't necessarily trust the reading. So there's a lot of challenges there. So we have found that there's a surprising number of tasks that we can kind of learn, implicit information about the forces being used, mostly just from vision. But I do think there is a gap there that better force sensors would help address for doing the really, really dexterous finding tasks. So I think that is important for the community to say.
Yeah, and I think the way that I've been thinking about this most is because I work so much on ego data. I think this really fits into the transferability aspect of human data. If you want, and so I think there's different schools of thought here. I think some people want to kind of are betting on sort of a humanoid robot plus human data. And the way for this kind of pipeline to work is that you solve a lot of these low level challenges on getting more direct transferability. And so I think for someone who would subscribe into this pipeline, you do probably want to invest more into this tactile because basically the issue is that if you don't, from the human data that you observe only visually, you just have state. And so, and you don't know the contact forces because you can't observe how hard the person is grabbing something. It's even harder because of two reasons. One is that the wrist cameras on robots provide a lot of this information because you can kind of sort of visually observe deformation. And the second thing is the state action gap, where on robot data, because you have a difference between your state and action, you can get some implicit level of effort being applied. But in human data, there's no such thing. It's just state. And so I think that for someone who is really trying to push on like zero shot ability of like dexterous human data to a humanoid robot trying to close all the gaps, that this will be critical. But if you're taking more of a cross-embodied approach, like it could be helpful, but like maybe not like 100% critical.
Just to add to that, I think in my mental picture, I kind of tend to separate them into two things. One is like the visual planning capability. You know roughly where you want to go, at least to establish context, so that you kind of at least get away with this like exploration problem, which will give you no signal if there's no contact or any interaction at all. I think that's the data that at least initially would be quite helpful, even though we're not technically collecting the fine grain, actually the actuation data. We're actually just collecting the realized action and the state. So I think that at least could be helpful, even though we're not collecting that data. And then the rest could either be delegated to let's say teleoperation or the domains where you can actually have the on robot sensing for actually the forceful information, etc. Yeah, so that's how I tend to separate it. That it's like visual planning and then also like force information. Yeah.
Also, I think there are several reasons that we do not have force data in our current data set. I guess one reason is that like this wave of robot learning is still quite young, I would say. So we are in the stage of just going through like very promising direction of how do we get generalizable behaviors using like commercially available arms or hands. So in this case, we like maybe many of us starting from CS background that we focus more on the learning side. How do we leverage the capability of models instead of capability of hardwares? So I guess this is one of the reasons we start by focusing on generalizations and then focusing on other aspects of robotics problems. And on the other hand, I think in the future, I mean, I recently observed a very fast growing trend of people focuses on forceful manipulations. And I guess this is people gradually realize there are several tasks that you cannot do very good by just leveraging position control. So I guess research-wise, there will be more and more interest. And there will be also, I mean, there has already been very good hardware with force-torque sensings, not only tactile sensings, but also joint force-torque sensors. That is like the price is getting much lower. And then I guess it will be very, very much widely available in future 1 or 2 years. And as a result, we will have more and more data of that type. And then we definitely we can incorporate these data into our current pipeline to make our robots much better in manipulation.
Hey, thank you. I think in the interest of time, we'll probably have one last question, and will be probably answered by 1 to 2 speakers. Anyone wants to ask the last one? Yeah.
Hello. I have a question about data quality control because in my team, we usually suffer from time mismatching and stuff like that, leading to chattering in the motion in the end. So I wonder, how do you check the data quality, especially if you have like teleoperation data and etc.
Yeah, Ashwin, do you want to talk about that?
Sure. Yeah. Yeah, I mean, I think there's, like, broadly speaking, like many axes of data quality you can consider. So I feel like, for example, with like Pi, like kind of the benefit is like, we can have like a pretty like complex like annotation pipeline that's like actually like doing like QA on like every part of like the data collection process. So there'll be things like obviously QA like okay, or like operators following basic instructions, like at that like kind of semantic level. And then even at the like low level, making sure that like, okay, like, do you have any like drop frames, dropped observations from like any sort of like modality that you should be logging, like all those things, like, you can like immediately flag. And I think like paying very careful attention to data quality is of course like very important. But like one thing we found with like py-07, for example, is that like, if there are aspects of data quality that like you can actually like observe cleanly from like labels you could collect post hoc, like you can actually like learn from some suboptimal, right? So for example, like if you have like, you know, like a missing wrist cam image and don't have that annotated, like, you know, your policy is obviously going to suffer, right? But you know, if you're like dropping that out a bunch and like retraining, like maybe that, right? But if you have like some like low quality behaviors of like someone like folding a t-shirt like very poorly, but you have like very detailed language annotations and like all of your robot data like describing like why that was done poorly, you might actually be fine. And I think like generally as a community, like as we're like scaling up robot data collection more and more and more, I think like of course we need to like have very careful data quality checks, but we also need to make sure we like make modeling and annotation decisions such that we can actually ingest low quality data, because like inevitably we're gonna have it.
Okay, cool. Anyone wants to add? Okay. If not, let's thanks our speakers for their great talks and great panels.
Okay. Thanks everybody. And now
Thank you.
thank you. We will now move to the award ceremony. Okay. And the Best Paper Award recognizes an outstanding contribution that is technically strong, clearly aligned with the workshop theme, and has strong potential impacts on data-centric robotics. And okay. Okay, and the best paper goes to Ambient Diffusion policy, imitation learning from suboptimal data in robotics. And let's welcome the author. Okay, let's take a picture together.
Stand in the middle.
Oh, sure.
Yeah.
Those are behind. 3, 2, 1. Okay, thank you.
Thank you.
Let's congrats the winning paper again.
We have a certificate. Wait.
I'll bring that back to Adam.
Okay. Thank you. I will finish this process. Okay. And okay, thank you for joining us. And thank you for joining us today. And thanks to our speakers and the authors, reviewers, organizers, and our sponsor, Spirit AI, and everyone here. And we hope today give you some new ideas about what robot data really need. And feel free to keep chatting with the speakers and the authors. Thank you.